July 1st, 2025. A telescope in Chile spots something moving at 130,000 miles per hour toward us, not from here, from another star. And suddenly, everyone's asking, what's the worst that could happen? Wherever you are right now, late night, early morning, somewhere in between, if you're curious about visitors from the void, you're in the right place. Tonight, we're following 3i Atlas through the darkness, chasing answers science gives us, and a few it's still working on. If this kind of wondering speaks to you, feel free to stay. Maybe leave a like, subscribe, if you want more nights like this, or just listen. Now then, let's meet our cosmic wanderer. The worst case scenario for 3i Atlas sounds insane until you consider this. What if it's not leaving? What if this flyby trajectory is actually a deceleration maneuver executed by technology we can't detect? Imagine an intelligence so advanced that mimicking natural orbital mechanics is child's play. A civilization that deploys surveillance assets disguised as comets, asteroids, even the cosmic debris we dismiss without a second glance. 3i Atlas's unprecedented speed and impossible chemistry might be signatures not of alien formation, but alien intention. As it approaches perihelion, hidden systems could be powering up, preparing for the next phase of whatever mission brought it here, across the void, between stars. The question isn't whether 3i Atlas will leave, it's whether we'll recognize the moment it decides to stay. On July the 1st, 2025, the Atlas Telescope Network in Chile detected something extraordinary. A speck of light moving against the stellar background, tracing a path through the constellation Lynx. That could only mean one thing: this visitor came from another star system entirely. Initially designated C2025N1, it would soon earn a more significant name, 3i Atlas, the third confirmed interstellar object to grace our solar system, following Oumuamua in 2017 and 2i Borisov in 2019. But what if this third visitor carries implications far beyond the first two? Implications that stretch the very definition of worst-case scenario into territories our instruments can barely map and our theories fear to tread. The defining characteristic appeared immediately in the orbital calculations. Unlike solar system natives bound by elliptical orbits, forever tethered to our sun's gravitational embrace, 3i Atlas traces a hyperbolic path through space. Its orbital eccentricity exceeds 1.0, marking it as definitively unbound to our sun's gravitational influence. This isn't speculation or preliminary data subject to revision. This is mathematical certainty, confirmed and reconfirmed by observatories worldwide. The object is racing inward from the constellation Lynx at speeds unprecedented, even among interstellar visitors, carrying momentum acquired across unimaginable distances and timescales that dwarf human civilization entirely. The numbers demand attention. Perihelion, the point of closest approach to our sun, will occur around October 29th at a velocity exceeding 130,000 miles per hour. To contextualize that almost incomprehensible speed, this object moves fast enough to cross the continental United States in under 3 minutes. Fast enough that if it somehow approached Earth directly, we'd have mere hours of warning before impact, though that particular nightmare scenario exists only in the realm of impossible physics. Yet beneath these dramatic velocities lies a more subtle mathematical truth. 3i Atlas's closest approach to Earth, occurring in mid-December, will be approximately 1.8 astronomical units away. That translates to roughly 270 million kilometers, nearly twice the distance between Earth and Mars at their closest approach. To put it another way, 50 times farther than our moon. NASA's position is unequivocal, stated clearly, and repeated across every official channel. This is a natural comet, not an artificial craft or hazardous object. The space agency's Planetary Defense Coordination Office conducted immediate risk assessment upon discovery, as they do with every newly detected near-Earth object and potential interstellar visitor. Their conclusion came swiftly and definitively: no threat to Earth exists. The mathematics of celestial mechanics are precise, unforgiving, and in this case, reassuring. The same hyperbolic trajectory that marks 3I Atlas as interstellar guarantees its safe passage through our cosmic neighborhood. But when we venture beyond NASA's careful language into the realm of speculation, what shadows might this ancient wanderer cast on our assumptions about intelligence, purpose, and cosmic coincidence? The Hubble Space Telescope has been monitoring the visitor since shortly after discovery, and what it's revealed should comfort us. Classic cometary behavior emerges as solar radiation sublimates the ices within the nucleus, creating that characteristic glowing coma we associate with objects from the outer solar system. This is exactly what natural comets do. The playbook is familiar, the signatures unmistakable. Then came August the 6th, when the James Webb Space Telescope turned its infrared gaze toward 3I Atlas and captured spectra that changed everything we thought we understood about this visitor. The data revealed something extraordinary, something that doesn't fit the comfortable patterns we've established through decades of studying comets, both near and far. The coma showed unusually high carbon dioxide concentrations, a chemical signature that speaks of alien formation conditions, unlike anything in our solar system. Not alien in the sense of artificial or designed, but alien in the truest meaning, foreign from elsewhere, shaped by stellar environments we've never directly studied. Yet this chemical oddity raises an uncomfortable question that will follow us through this entire investigation. What if 3I Atlas's true significance lies not in what it is, but in what it forces us to confront about what we don't know? Ground-based observatories worldwide have joined the coordinated observation effort. Radio telescopes have swept across the object's position, listening for coherent signals that might betray artificial origin. They've found only natural emission, so only the electromagnetic silence we expect from sublimating ice and dust interacting with the solar wind. This coordinated response represents modern astronomy at its finest, a global network of scientists and institutions working in concert, confirming both the object's interstellar origins and its apparently harmless trajectory. But what happens when we push beyond the comfortable boundaries of apparently harmless and consider scenarios that challenge not our physical safety, but our fundamental understanding of our place in the universe? The discovery frequency suggests something profound about the nature of interstellar space. If 3 confirmed interstellar objects have passed through our solar system in just 8 years, how many do we miss? How many slide past, undetected because they're too small, too dark, or approaching from angles our surveys don't adequately cover. The galaxy, it seems, teems with such wanderers. Debris from planetary formation around distant stars flung into the void by gravitational violence and condemned to wander for billions of years. Each one teaches us something new about the galaxy beyond our sun's influence, about the diversity of materials and conditions that exist in stellar neighborhoods we can barely imagine. Though none threatens our world's safety directly, their very existence reshapes our understanding of cosmic architecture. As The Guardian aptly noted in their coverage, 3i Atlas is a cosmic curiosity, not a catastrophe, a reminder that we inhabit a universe far stranger and more connected than daily life suggests, where objects born around other stars can arrive at our doorstep, carrying secrets from galactic deep history. This ancient visitor offers us a brief window, a fleeting opportunity to study materials and chemistry from environments we may never visit directly. But what if the real mystery isn't what secrets it carries forward from the past, but what secrets it might unlock about the true nature of interstellar visitors and the speculative scenarios that lie tantalizingly beyond the reach of our most powerful telescopes? While you've been reading these words, taking perhaps 5 seconds to process each sentence, iAtlas has traveled 180 kilometers through the void. That's roughly the distance from Hanoi to Ninbin, covered in the time it takes you to read a paragraph. The scale of cosmic motion operates on levels that our terrestrial experience struggles to process. Yet the mathematics tracking this visitor's every movement remains precise to within kilometers, across distances measured in astronomical units. NASA's reassurance that 3i Atlas poses absolutely no danger might sound familiar in an unsettling way. It's like a doctor saying, "just a small pinch," before an injection, a phrase we've all learned to interpret with healthy skepticism. But here's the thing, this time NASA is absolutely right. The margins aren't close. The mathematics aren't uncertain. This is as safe as cosmic encounters come confirmed by multiple independent observations and calculations performed by institutions across the globe using different methodologies that all arrive at identical conclusions. And yet, try to wrap your mind around the velocity for a moment. 130,000 miles per hour sounds abstract, doesn't it? Let's ground it in something more tangible. A high-powered rifle bullet travels at roughly 3,000 kilometers per hour. That's fast enough to be invisible to the human eye, fast enough to cross a football field in a fraction of a second. 3i Atlas moves 150 times faster than that bullet. If you could somehow drive a car at this speed from Hanoi to Saigon, the journey would take precisely 4 seconds. 4 seconds to cross the length of Vietnam. That's not just fast, that's physics, operating at scales that make our everyday experience feel almost quaintly slow. Let's slow down for just a moment. Breathe. These numbers can feel overwhelming, like trying to hold an ocean in your hands. But that's exactly why we're here, isn't it? To make sense of the incomprehensible, one careful step at a time. Ready? Let's dive deeper into what these numbers actually mean. The velocity alone staggers the imagination, but let's be precise about what we're actually observing. 3i Atlas moves at more than 130,000 miles per hour. which translates to roughly 210,000 kilometers per hour. Or if you prefer the units, astronomers favor 61 kilometers per second. This is what scientists call the hyperbolic excess velocity, the speed it maintains even after accounting for the sun's gravitational influence, unchanged by eons of galactic wandering. This represents kinetic energy accumulated across timescales that make human civilization look like a brief flicker momentum that has persisted perhaps for billions of years, as this object traced its lonely path through the darkness between stars. This velocity absolutely dwarfs its interstellar predecessors, and the comparison reveals something potentially significant. Oumuamua, that first confirmed visitor that sparked so much speculation and wonder back in 2017, traveled at 26 kilometers per second, already impressively fast by any terrestrial standard, but modest compared to what came after. 2I Borisov, discovered in 2019, managed 32 kilometers per second, still substantial, but 3I Atlas nearly doubles that figure at 61 kilometers per second. This progressive increase demands explanation. Either these objects were ejected with tremendous violence from their birth systems, flung out by gravitational encounters with massive planets or stellar companions, or they've been accelerated through multiple gravitational encounters during their cosmic odyssey, each close pass by a star or massive object, adding or subtracting velocity in a cosmic game of gravitational billiards played across galactic distances. Yet what if this progressive increase in velocity across our three confirmed interstellar visitors hints at something more deliberate than random cosmic violence? What if there's a pattern here that pushes us toward speculative territories our instruments cannot explore and our current theories cannot adequately address? These are the questions that keep astronomers awake long after their observing shifts, and the uncomfortable possibilities that lurk at the edges of conventional explanation. Determining the actual size of 3I Atlas proves frustratingly challenging, and this uncertainty matters more than you might initially think. Current estimates range from 0.3 to 5.6 kilometers in diameter. That's a tremendous spread, anywhere from roughly 3 football fields laid end to end up to a small mountain. To put that in perspective, if 3I Atlas is at the small end of the estimate, it's about the size of a large urban neighborhood. At the high end, it would dwarf Mount Vesuvius. The uncertainty stems from assumptions about surface reflectivity and the efficiency of coma production. Without knowing precisely how much of the sunlight hitting the nucleus gets reflected versus absorbed, and without understanding exactly how efficiently the sublimating ice produces the glowing coma, we observe pinning down the size becomes an exercise in calculated guesswork. The smaller estimates seem more likely based on typical comet parameters and the brightness we observe, though even at 0.3 kilometers, we're discussing a substantial object, something the size of a large asteroid, carrying enough mass and material to have survived whatever ejection event sent it on its interstellar journey. But what if the very uncertainty that frustrates our measurements conceals possibilities that extend far beyond questions of mere size? What if not knowing the precise dimensions leaves room for speculation about internal structure, composition, and purposes that might transcend natural explanation entirely. This size uncertainty raises fascinating questions about cosmic survival. How could such a relatively modest body endure the violence of ejection from its home system, followed by millions or potentially billions of years, exposed to the harsh conditions of interstellar space? Smaller objects face greater vulnerability to tidal disruption during close encounters with massive bodies. They're more susceptible to being shattered by high-speed impacts, with cosmic debris more likely to be affected by radiation pressure and stellar winds. Yet, 3I Atlas endures apparently intact, apparently functional, according to all our observations. What does this survival tell us about its composition, its structure, its origins? And when we venture beyond asking how it survived into questioning whether survival itself might hint at something extraordinary, what speculative doors open before us? Most intriguingly, analysis suggests 3I Atlas likely possesses extreme antiquity. The evidence comes from its motion relative to galactic rotation, a subtle but revealing signature. Most objects in our local stellar neighborhood move with the galaxy's spin, following roughly circular orbits around the galactic center like cars on a cosmic roundabout. But 3I Atlas approaches from an unusual angle, suggesting membership in an older, more randomly oriented population. These are stellar seniors, ancient objects whose orbits haven't been tidied by billions of years of galactic evolution. If this interpretation proves correct, our visitor could predate our entire solar system by billions of years, carrying within its nucleus records of galactic evolution from when the universe itself was less than half its current age. Let that temporal scale sink in for a moment. 5 billion years is not a number the human mind processes easily. Here's one way to think about it. If each year were compressed into 1 second, 3I Atlas would have been traveling for 158 years. In that same compressed timescale, all of recorded human history would last about 3 minutes. The pyramids of Egypt were built roughly 45 seconds ago. The entire span from the first human civilizations to the present moment equals about 3 minutes in a journey lasting nearly 2 centuries. We are Johnny-come-latelys to a universe that was already ancient and complex long before our sun ignited, studying an object that may have begun its journey when our solar system was nothing but a diffuse cloud of gas and dust beginning its slow gravitational collapse. But what if this ancient origin story becomes the foundation for speculative scenarios that challenge our understanding of time, purpose, and cosmic intelligence itself? The thick disk interpretation emerges from careful analysis of 3I Atlas's velocity vector and its angle relative to the plane of the galaxy. While younger stellar populations in the thin disk where our sun resides move in relatively orderly co-rotating patterns, the thick disk contains stars and presumably ejected planetary debris with more chaotic inclined orbits. These are fossils from the galaxy's youth, from a more violent era of star formation and stellar evolution. Finding an interstellar visitor from this population is like receiving a message in a bottle thrown into the cosmic ocean billions of years ago, long before anyone was here to receive it. Yet when we venture beyond astronomical interpretations into speculative territory, what might this unusual approach angle suggest about intentionality, about navigation, about purposes that extend beyond natural orbital mechanics, governed purely by gravity and momentum. Despite tremendous speed and mysterious history, 3I Atlas poses no dynamical threat, and we must keep returning to this reassuring truth. The same hyperbolic trajectory, marking it as interstellar guarantees safe passage. It moves too fast for solar gravity to capture it, too fast to be deflected significantly by any planetary encounter. Closest approach distances are measured in astronomical units, not kilometers. At perihelion, around October 29th, it will skim past at roughly 1.4 astronomical units from the Sun, placing it between Earth's orbit and Mars's orbit, close enough for significant solar heating and spectacular carbon dioxide coma production, but nowhere near affecting planetary orbits or raining debris on any inhabited world. Observing windows present their own challenges, adding urgency to every measurement and spectrum captured. Peak brightness will reach only about magnitude 11, requiring telescopes, even under perfect observing conditions. No casual sky gazer will catch a glimpse of this visitor, despite its tremendous size and speed. During its closest solar approach, the object will disappear entirely into our star's glare, hidden in the brilliance of the Sun, precisely when it becomes most active, when sublimation rates peak and the coma expands to its maximum extent. This is cosmic timing that feels almost cruelly coincidental, as if the universe designed this encounter specifically to frustrate detailed study during the most interesting phase. Yet what if this observational limitation becomes the gateway to speculative scenarios, where what we cannot see matters more than what we can measure with confidence? What emerges from all these numbers and uncertainties is a portrait of cosmic endurance that challenges easy categorization. 3I Atlas embodies the intersection of impressive physics and mundane risk, reminding us that the universe operates on scales, dwarfing everyday experience while following laws precise enough to predict this visitor's location years in advance with accuracy measured in kilometers. But when we dare to ask, what lies beyond these predictable trajectories? What speculative worst-case scenarios emerge that have nothing to do with orbital mechanics and everything to do with cosmic revelation? Trying to imagine 5 billion years is an exercise in futility, for minds evolved to track seasons and decades. But try this: if every year of 3I Atlas's potential age were 1 second, the object would have been traveling for 158 years. Meanwhile, all of human history, from the first agricultural settlements to this very moment, would occupy about 3 minutes of that time span. Everything we've ever built, every empire risen and fallen, every discovery made and forgotten and rediscovered, all of it compressed into 3 minutes against a journey lasting nearly 2 centuries. That's the scale we're dealing with, the temporal vastness that makes our civilizational concerns feel almost touchingly provincial. The challenge of determining 3I Atlas's exact size might sound like a technical problem of purely academic interest, but there's something almost poetic about it. It's like trying to guess someone's weight from a blurry photograph on social media. You've got some clues, certain indicators, but commit to a specific number at your peril. The consequences of being wrong about a person's weight are social embarrassment. The consequences of being wrong about 3I Atlas's size affect our understanding of how much material was ejected from its home system, how much mass it's retained during its journey, and by extension, what that tells us about the violence and conditions of its origin. And speaking of origins, this business about the thick disk deserves one more grounding metaphor. Imagine Hanoi. The old quarter is like the galaxy's thick disk, ancient chaotic streets, winding in patterns that predate modern planning buildings, that have stood for centuries, bearing witness to countless changes. The new urban developments outside the city center, those are like the thin disk, younger, more organized, laid out in grids that reflect contemporary understanding of efficient city planning. 3i Atlas comes from the old quarter of the universe, from neighborhoods that formed when the cosmos was young and wild and still figuring itself out. Understanding this visitor means trying to read a dialect of cosmic chemistry that was spoken before our sun learned to shine. 2 parts down, we've established what 3i Atlas is, where it came from, and why the numbers make even astronomers pause. But there's something else that makes this visitor's truly strange. Something about its chemistry that doesn't quite fit the pattern. Shall we? When the James Webb Space Telescope turned its infrared eye toward 3i Atlas on August 6th, the data that came back wasn't just unusual, it was shocking in ways that make even veteran astronomers lean forward in their chairs and question their initial assumptions. The coma, that glowing envelope of gas and dust surrounding the nucleus, revealed itself to be dominated by carbon dioxide, not merely enriched in CO2, not showing elevated levels, dominated. The ratio of carbon dioxide to water came in at approximately 8:1. 8 parts carbon dioxide, 1 part water. This wasn't just abnormal. This was unprecedented in the entire history of cometary chemistry. But as we prepare to venture beyond chemical analysis into speculative territory, what if this molecular signature hints at purposes and origins that stretch far beyond natural formation processes we currently understand? Let's establish what normal looks like first, because context matters when we're discussing how profoundly 3i Atlas breaks the mold. Typical comets follow predictable scripts that we've refined through the decades of close observation. Water ice dominates their composition, sublimating at modest temperatures to create the classic water vapor comas we see through telescopes mixed with dust particles that scatter sunlight and create those beautiful tails stretching across the sky. The molecular sequence follows an established pattern. Water appears first as the comet approaches the sun, followed by carbon monoxide at slightly closer distances, then carbon dioxide, and finally trace compounds in minute quantities. These molecular ratios tell stories, encoding information about formation conditions billions of years ago and evolutionary history across the lifetime of the solar system. But 3i Atlas has rewritten this script entirely. It breathes carbon dioxide, like atmospheric production, on an industrial scale, as if someone designed a factory optimized for CO2 output, rather than the balanced mixture we expect from natural icy bodies. And what if this deviation from the norm opens doors to speculative scenarios that challenge everything we assume about natural versus artificial origins? The numbers become even more striking when we consider the observation distance. 3i Atlas was over 3 astronomical units from the Sun, well beyond Mars's orbit. when Webb captured its spectrum. At this range, most comets show little to no activity. They're essentially dormant, too far from the sun's warmth to generate significant sublimation. The ices remain frozen, locked in place by the extreme cold of deep space. Yet here was 3I Atlas producing a detectable carbon dioxide-dominated coma extending hundreds of thousands of kilometers from its nucleus. This shouldn't be possible, according to conventional understanding. The solar heating at that distance simply isn't sufficient to drive such vigorous activity from a typical comet. But what if this inexplicable activity at impossible distances becomes the foundation for speculative scenarios about energy sources, internal mechanisms, and purposes that transcend our current understanding of what's naturally possible? Several theories attempt explanation, and we should examine them carefully before venturing into more exotic territory. First, 3I Atlas might have formed near its natal star's CO2 snowline, that specific distance where temperatures allow carbon dioxide to preferentially condense from the protoplanetary disk, while water remains in vapor form or forms farther out. This would bake in a CO2-rich composition from birth, a chemical signature of formation conditions radically different from those in our own solar system. Alternatively, extreme age and cosmic ray processing could have modified surface chemistry over billions of years. Radiation bombardment creates radiation-processed crusts that seal water beneath the surface while allowing more volatile CO2 to percolate through and escape. Think of it as cosmic weathering that fundamentally alters the chemical architecture of the object's outer layers. A third scenario involves insulating dust mantles developed over geological time, acting like cosmic insulation that prevents water ice from accessing surface heat while allowing carbon dioxide's percolation through microscopic channels and fractures. Yet what if all these natural explanations, however plausible and well supported by physics, miss the most unsettling possibility that this chemical signature represents something deliberately engineered for purposes we cannot yet comprehend? Webb's near-infrared spectrograph detects molecular fingerprints with extraordinary precision, revealing details invisible to optical telescopes or even earlier infrared instruments. When sunlight heats the coma, molecules absorb and re-emit light at specific wavelengths determined by their atomic structure and vibrational modes. Each molecule has its own unique spectral signature, as distinctive as a human fingerprint. The observed 8-to-1 ratio represents one of the most extreme CO2 enhancements ever recorded in cometary observations, either from our solar system or beyond. But when we push beyond spectroscopic measurements into speculative territory, what if these molecular signatures encode information that extends far beyond simple chemistry, messages perhaps embedded in ratios that seem designed to attract attention, or indicators of purposes that challenge our assumptions about cosmic intelligence and how it might choose to communicate or mark its presence? This chemistry isn't entirely unprecedented, which provides both context and raises further questions. Comet C2016R2, also known as Pan-STARRS, displayed atypical volatile ratios during its passage through our solar system several years ago. That object showed unusual carbon monoxide and nitrogen concentrations that didn't match standard cometary models. Such chemical outliers suggest either more diverse comet formation processes than theories initially assumed, or dramatic post-formation processing that can alter surface compositions in fundamental ways. Yet as we approach the realm of pure speculation, what if these chemical anomalies across multiple objects hint at a pattern rather than random variation? What if they represent a signature that points toward possibilities existing beyond the comfortable boundaries of natural explanation, possibilities that would require us to fundamentally rethink our assumptions about what's possible in the cosmos? The true value of 3I Atlas lies in what it represents chemistry from entirely different stellar environments. While pan-stars formed under conditions we can model based on our understanding of our own solar system's formation, this interstellar visitor carries chemical signatures from processes around different stars, possibly billions of years ago, when galactic chemical abundances differed from today's. It's alien geology delivered to our doorstep, a sample we never had to launch a spacecraft to collect. But what if this delivery is less accidental than we assume? And what speculative scenarios emerge when we consider that ancient intelligence might have found ways to encode information in the very chemistry we're now detecting using molecular ratios as a form of communication that persists across billions of years? Ongoing observations will determine whether CO2 dominance represents bulk composition throughout the nucleus or merely surface expression of deeper, more complex layering. As solar heating increases during approach to perihelion, molecular balance may shift if water ice lies beneath CO2-rich surface layers. Increasing thermal penetration could reveal deeper compositional layers, allowing us to effectively take a core sample through remote spectroscopy. Yet what if these changing chemical signatures, as 3I Atlas approaches perihelion, reveal patterns that suggest not random heating effects, but systematic activation? What if the spectra show variations that correlate too perfectly with solar distance to be coincidental, opening pathways to speculative scenarios about dormant systems awakening under solar influence mechanisms designed to respond to specific environmental triggers in ways that transcend natural sublimation processes? From broader perspectives, this unusual chemistry tests planetary formation models, extending far beyond our solar system. If theories about icy body formation and evolution are correct, they should account for the observed diversity in interstellar visitors. 3I Atlas challenges expectations, suggesting either theoretical gaps in our understanding or simply vast ranges of conditions in galactic neighborhoods we've never studied directly. Yet when we venture beyond theoretical frameworks into pure speculation, what if the challenge this visitor presents to our models hints at something more profound? Evidence of processes, purposes, and intelligences that operate beyond the natural laws we've spent centuries mapping with ever-increasing precision. What does an 8-to-1 ratio actually mean in tangible terms? Imagine your morning coffee. Normally, you might mix equal parts coffee and milk, or perhaps favor one over the other by a small margin. Now imagine 8 parts milk to 1 part coffee. Would you even call that coffee anymore? Or has it become something else entirely? That's 3i Atlas in the world of comets so far outside the normal range that we question whether our categories still apply, whether the frameworks we've built to understand these objects remain adequate when confronted with chemistry this extreme. When Webb looked at 3i Atlas and captured those spectra, it was like running into an old friend after a decade apart and realizing they've changed so fundamentally that you barely recognize them. The awkward moment where you want to say something, but all that comes out is, "Wow, you've really changed." That's essentially where the astronomical community found itself staring at data that fit the category of comet, but violated so many expectations about what comets should look like chemically that a moment of collective cognitive dissonance rippled through the field. We're now at part 3 of Act 1, and you might be wondering why we're spending so much time discussing carbon dioxide ratios and molecular chemistry. Here's why this is the detail that keeps astronomers awake at night. The data point that doesn't quite fit the anomaly, that whispers questions we're not sure we're ready to answer. When scientists lose sleep over observations, when data makes them uncomfortable enough to double and triple check their instruments and calculations, that's usually a sign that something interesting is happening, something worth paying very close attention to, whether it ultimately leads to revised theories about natural processes or opens doors to possibilities we haven't yet dared to seriously consider. That chemistry tells us 3i Atlas is strange, beautifully, fascinatingly strange. But strange doesn't mean dangerous. In fact, as we're about to see, the actual worst-case scenario isn't scary at all. It's almost disappointingly mundane. Almost. Let's talk about what the math actually says. Nearly 2,000 words into our investigation, we arrive at what was supposed to be the terrifying climax, the moment where we confront the genuine worst-case scenario. And here's the truth that might feel anticlimactic, but should actually bring profound relief. There really isn't one. Not in the Hollywood sense. Not in the civilization-ending, planet-destroying, gravity-disrupting sense that our primitive threat detection systems might fear when hearing about objects racing toward our solar system at impossible speeds. No catastrophe awaits. No collision threatens Earth. No gravitational disruption will send our planet careening into the sun or fling it into the frozen darkness of deep space. Cold, precise, celestial mechanics delivers a verdict that should help us sleep peacefully through the night. Yet, as we prepare to venture beyond the safety of scientific certainty, what if the real worst-case scenarios exist not in the realm of physics, but in the speculative shadows, where our instruments cannot reach and our theories fear to tread? Those crucial numbers deserve repetition because they form the bedrock of reassurance, upon which everything else builds. 3i Atlas approaches no closer than 1.8 astronomical units to Earth. That translates to 270 million kilometers of comfortable buffer, a distance that exceeds twice the Earth-Mars closest approach and represents more than 50 times the distance to our moon. These aren't rough approximations, subject to revision as more data arrives. These are precise orbital calculations, accounting for major planetary gravitational influences, relativistic effects that become relevant at these velocities, and subtle perturbations from radiation pressure, as sunlight itself exerts minuscule but measurable forces on the object's trajectory. Perihelion, the closest approach to our Sun, occurs around October 29th, 2025, at approximately 1.4 astronomical units. This places 3I Atlas between Earth's orbit and Mars's orbit, close enough for significant solar heating that will drive spectacular carbon dioxide coma production, creating a display that professional astronomers will study intensively with every instrument at their disposal. But this is nowhere near close enough to affect planetary orbits or rain debris onto any world in our solar system. The gravitational influence of this relatively small object, even moving at tremendous velocity, simply cannot overcome the massive stabilizing presence of the Sun and the established orbital mechanics that have governed our solar system for 4.5 billion years. But what if distance becomes irrelevant when we consider speculative scenarios involving technologies, intelligences, or purposes that operate beyond the constraints of physical proximity, that function according to principles we haven't yet discovered? When astronomers declare that 3I Atlas poses no threat, they speak with confidence built from centuries of celestial mechanics and decades of experience tracking potentially hazardous objects. This isn't casual reassurance or bureaucratic hand-waving designed to prevent public panic. This is mathematical certainty, confirmed by independent calculations performed at institutions worldwide using different methodologies that all converge on identical conclusions. The Planetary Defense Coordination Office, NASA's dedicated program for identifying and tracking near-Earth objects that might pose impact risks, conducted immediate assessment upon 3I Atlas's discovery. Their conclusion came swiftly and unambiguously. No threat exists. The orbits don't intersect. The distances remain comfortably large. The velocities, while impressive, work entirely in our favor. Yet what if the calculations that ensure our physical safety become the very foundation for speculative, worst-case scenarios that have nothing to do with collision and everything to do with contact communication and cosmic revelation? The initially alarming speed at 130,000 miles per hour that sounds so threatening when first encountered actually works to our advantage in unexpected ways. Objects on hyperbolic trajectories moving at such velocities cannot be captured by solar system gravity. The mathematics are unforgiving on this point. 3I Atlas moves too fast to linger and cause trouble, even if it somehow possessed malicious intent, which, of course, natural comets do not. It's performing its cosmic flyby according to laws of physics that care nothing for human concerns or fears, and then it will disappear back into interstellar space, headed for some other stellar neighborhood that it might reach in another few million years. But what if this very speed, this inability to be gravitationally captured, represents something more than natural orbital mechanics? What if it hints at deliberate design, at precise timing, calculated to achieve specific observational goals, while maintaining plausible deniability about artificial origin? What if it suggests purposes that extend far beyond our current ability to detect or comprehend? This highlights important risk communication, distinctions that space agencies navigate carefully and with admirable transparency. The word interstellar carries emotional weight entirely unrelated to actual danger. Our primitive brain structures evolved to detect and respond to immediate threats in our ancestral environment don't naturally process the geometric realities of vast space and precise orbital mechanics. We hear object racing toward us from another star, and ancient threat detection systems activate, preparing us for danger that doesn't actually exist. The vast scales of space and the mathematical precision of orbital mechanics conspire to make such encounters fascinating rather than dangerous, intellectually stimulating rather than existentially threatening. Yet what if our focus on physical danger blinds us to other kinds of risks, the speculative scenarios, where the worst case isn't about what 3i Atlas might do to us, but what it might reveal about us, our assumptions and our place in a universe far stranger than we dare imagine. NASA's communications strike a perfect balance that deserves recognition and praise. They acknowledge the scientific significance of 3i Atlas while emphasizing the complete absence of hazard. Clear jargon-free language explains why this object proves remarkable without being threatening, maintaining genuine public interest in authentic discovery while avoiding the creation of unnecessary anxiety. This represents science communication at its finest, threading the needle between exciting the imagination and managing reasonable expectations about both risks and potential revelations. Previous interstellar visitors provide additional context that reinforces these reassurances. Oumuamua posed no threat in 2017, despite unusual behavior that sparked intense speculation. 2i Borisov displayed entirely predictable cometary activity during its 2019 passage, behaving exactly as cometary physics predicted it should. 3i Atlas continues this pattern of scientifically fascinating but dynamically harmless visitors objects that expand our knowledge while posing no danger to our world. But as we stand at the threshold of speculation, what if this pattern of harmless visitors masks something far more significant? What if we're witnessing not random encounters, but a cosmic census, a gradual revelation that challenges everything we think we know about intelligence, purpose, and our cosmic neighborhood? What if the very harmlessness represents deliberate design, a strategy for observation that avoids triggering defensive responses from emerging technological civilizations like our own? Our current understanding forms a satisfying foundation built on extensive observation and rigorous analysis. We know 3i Atlas's speed with precision. We've mapped its trajectory with accuracy. We understand its unusual CO2-rich composition, even if certain aspects remain puzzling. We have compelling evidence suggesting great age and thick disk galactic origins, placing this visitor's birth in an earlier epoch of our galaxy's evolution. Multiple world-class telescopes have provided detailed observations of chemical makeup and physical behavior, creating a comprehensive data set that will fuel research papers for years to come. These knowns paint a picture of an ancient, fast-moving, chemically unusual, but fundamentally natural comet and object that fits within our understanding of how the universe operates, even while pushing the boundaries of that understanding in interesting directions. Important unknowns remain, of course, because science always involves uncertainties and questions that future observations might resolve. precise nuclear size. Estimates range from hundreds of meters to several kilometers, a frustrating spread that reflects the challenges of observing small distant objects surrounded by glowing comas. Surface versus bulk composition. Explanations for CO2 dominance remain unclear, requiring observations at multiple epochs and possibly close spacecraft encounters that won't happen during this particular passage. We cannot pinpoint the natal stellar system with certainty, cannot reconstruct the precise gravitational encounter sequences that shaped the current trajectory. Crucially, though, none of these unknowns affect the risk assessment. The safety margins remain comfortable, regardless of whether the nucleus measures 300 meters or 5 kilometers across, regardless of whether the CO2 enrichment represents bulk composition or surface processing. But what if these unknowns become the foundation for speculative scenarios that push far beyond the comfortable boundaries of natural explanation? Visual evidence tells consistent stories across multiple independent instruments and observation campaigns. Hubble's images show classic cometary signatures: a glowing coma surrounding a central nucleus, tails forming as radiation pressure pushes gas and dust away from the sun. Webb's spectra reveal unusual but demonstrably natural chemical compositions, molecular signatures that match patterns we associate with sublimating ices rather than industrial processes or technological systems. Ground-based observations track predictably evolving emissions that correlate precisely with solar distance and heating exactly as cometary physics predicts. No artificial signals appear in the data. No thermal signatures suggest active power generation beyond solar heating. No controlled maneuvers reveal themselves in the trajectory. Yet what if this very absence of obvious artificiality becomes the doorway to speculative scenarios about intelligence so advanced, so subtle, that it operates beyond our current ability to detect or recognize? Every measurement points toward identical conclusions from independent researchers using different instruments and methodologies. 3I Atlas represents what it appears to be a natural comet carrying alien stellar environment chemical signatures while behaving according to universal physical laws that operate the same way here as they do in distant star systems. This universality confirmation represents one of astronomy's most profound discoveries. This realization that the same physics governing our local environment applies across cosmic distances and throughout cosmic history, and the worst-case scenario, defined narrowly in terms of measurable physical threats to Earth, stands thoroughly debunked. The mathematics remain clear. The observations stay consistent. The conclusions provide reassurance. This cosmic visitor comes in peace intentionally, or not simply following the orbital path determined by its velocity and the gravitational architecture of our solar system. But now comes the moment where we step deliberately beyond the safety of scientific consensus into the realm of pure speculation, where worst-case scenarios take entirely different forms. Not threats to our bodies or our planet's stability, but challenges to our understanding of what's possible in a universe that may be far more populated, far more intelligent, and far more purposeful than our current models dare suggest. We're about to venture into territories where instruments fall silent and theories become uncomfortable where questions multiply faster than answers, and certainty gives way to productive uncertainty that drives science forward into new territories of investigation and discovery. 270 million kilometers sounds safe in the abstract, doesn't it? A number so large, it loses meaning. Here's a way to make it tangible. If you could drive a car at 100 kilometers per hour without stopping, never pausing for fuel, or rest maintaining that speed, constantly, it would take 308 years to cover that distance. You'd need to start driving in 1716 during Vietnam's Lei Dynasty, and you'd arrive right about now. That's how far 3I Atlas will be at closest approach. That's the buffer zone that makes this encounter fascinating rather than frightening. NASA saying 3I Atlas is absolutely safe might trigger a familiar skepticism, like an ex-partner texting, "Just passing through, won't stop by." A message that history has taught us to interpret with healthy caution. But here's the thing this time, they're absolutely right. No stopping by, no unexpected visits. Just a clean flyby with numbers that leave no room for doubt or revision. And that speed, that tremendous 130,000 miles per hour velocity, that seems so threatening. It's actually our protection. Think of it like running past an old friend's house at 200 kilometers per hour. Even if some part of you wanted to stop, wanted to veer off course and drop in for a visit, the physics simply wouldn't allow it. You'd need the brakes beyond anything currently possible. 3I Atlas faces the same constraint with the sun's gravity. It's moving too fast to stop too fast, to be captured too fast to do anything but pass through and continue on its billion-year journey to wherever momentum and gravity eventually take it. The threat isn't real. It never was. But the questions it raises about what else might be out there, about what other visitors might arrive with different velocities and different purposes, those questions persist, hanging in the space between confirmed safety and speculative possibility, between the universe we understand and the universe we're still learning to see. We've established safety. We've examined the strange chemistry. Now comes the part where we ask the uncomfortable questions, where we dare to wonder not just what 3I Atlas is, but what it might mean if we're wrong about everything. Ready to go deeper? Part 5 awaits. Now, we step deliberately across a threshold, from established fact into the realm of speculation, where possibilities multiply, like reflections in a hall of mirrors, where certainty gives way to productive uncertainty that drives science forward into territories our instruments can barely map, and our theories haven't yet learned to navigate. Everything that follows should be understood as thought experiment rather than scientific conclusion, a mental journey into what might be clearly distinguished from what we actually know, with confidence built on observation and measurement. The evidence we've established, examined carefully across 4 detailed sections, points overwhelmingly toward 3I Atlas being a natural comet, an ancient wanderer carrying exotic chemistry from stellar environments we've never visited. But let's explore what it would mean if that evidence was somehow incomplete, if our observations missed something crucial, or if our interpretations, however well supported by physics and precedent, led us astray in ways we haven't yet recognized. The baseline remains unchanged, and we must anchor ourselves to this reality Before venturing into speculation, NASA, the European Space Agency, and virtually every mainstream astronomical institution describe 3I Atlas as a natural cometary visitor, an assessment reached through rigorous analysis, using multiple independent instruments and methodologies. This isn't bureaucratic groupthink or scientific conservatism, for its own sake, some institutional unwillingness to consider extraordinary possibilities. This is the conclusion that best fits the available data, the interpretation that requires the fewest assumptions and invokes no physics beyond what we already understand. The object displays classic cometary behavior, sublimating ices, producing a glowing coma, predictable responses to solar heating spectroscopic signatures consistent with natural materials. It follows predictable orbital mechanics, tracing the hyperbolic path that gravity and momentum dictate with precision that allows us to predict its position years in advance. Occam's razor, that fundamental principle of scientific reasoning that guides us towards simpler explanations when multiple interpretations exist, strongly favors the natural explanation. We should not multiply entities. Beyond necessity, should not invoke exotic mechanisms when mundane ones suffice. But science has a history of surprises moments when the universe proved stranger than our careful theories predicted, when observations forced us to expand our understanding in directions we hadn't anticipated. Some of the most significant discoveries came from objects that initially appeared entirely mundane, utterly unremarkable, until closer examination revealed their true nature. Consider pulsars, those rapidly spinning neutron stars that produce lighthouse-like beams of radiation sweeping across space with metronomic precision. When first detected in 1967, these mysterious radio signals arrived so regularly, with such uncanny timing, that astronomers briefly designated them LGM for Little Green Men, half-jokingly entertaining the possibility that they'd stumbled upon alien beacons before recognizing them as signatures of exotic stellar remnants, dead stars compressed to impossible densities and spinning at rates that challenged imagination. Or consider fast radio bursts, those brief intense pulses of radio emission that baffled astronomers for years, their origins mysterious and their properties defying easy explanation before eventually revealing themselves as signatures of cosmic phenomena involving neutron stars and magnetic fields of almost incomprehensible strength. Could 3I Atlas represent another example of nature, proving stranger than our initial assumptions? Another case where the mundane explanation gives way to something more exotic, if not artificial, then at least profoundly different from what we expected. The speculation about artificial origins doesn't emerge from a vacuum or from fringe voices operating outside mainstream science. Avi Loeb, the Harvard astrophysicist who gained considerable attention for his unconventional interpretations of Oumuamua, that first confirmed interstellar visitor whose elongated shape and slight acceleration sparked intense debate, has already begun floating similar possibilities for 3I Atlas in various interviews and blog posts. Loeb's position, clearly labeled as opinion rather than established fact, suggests we should remain open to the possibility that some interstellar objects might represent technology rather than natural phenomena, that among the cosmic debris wandering between stars, We might occasionally encounter artifacts from civilizations that achieved interstellar capability. This perspective deserves serious consideration, not because it's necessarily correct or even probable, but because it illustrates how we should evaluate extraordinary claims with rigorous standards, yes, but also with minds open enough to recognize genuinely unprecedented discoveries when they occur without dismissing possibilities simply because they challenge comfortable assumptions. What would constitute convincing evidence for artificial origin? What observations would force us to abandon the natural comet hypothesis in favor of something more exotic, to accept that we're dealing with technology rather than geology? These questions matter because they help us distinguish between healthy scientific skepticism and reflexive dismissal of unconventional ideas. First, coherent radio emissions would represent perhaps the most obvious technological signature, indicating onboard electronics or communication systems attempting to transmit information across interstellar distances. Such signals would need to be clearly artificial in origin, not the random electromagnetic noise that all objects emit through natural processes, but structured transmissions displaying modulation patterns or information content that couldn't arise from sublimating ice and solar wind interactions. Radio telescopes have been listening, sweeping across 3I Atlas's position, with sensitive receivers capable of detecting signals far weaker than our own radio broadcasts, and they've found only silence, only the natural electromagnetic whispers we expect from cometary material interacting with its environment. Second, non-gravitational accelerations inconsistent with outgassing would represent another telltale signature of artificial propulsion. Natural comets often show slight deviations from pure gravitational trajectories, as sublimating gas creates tiny thrust forces, rocket effects in miniature, as material streams away from the nucleus. But if 3I Atlas were to change velocity in ways that couldn't be explained by gas production rates, or if its acceleration didn't correlate properly with solar heating patterns that should drive sublimation, that might suggest some form of propulsion system, some mechanism for controlled trajectory adjustment that operates beyond natural processes. So far, the trajectory follows celestial mechanics without unexplained deviations, each position measurement fitting predictions derived from gravity and momentum with accuracy that leaves no room for mysterious forces. Third, engineered light curves might provide additional evidence, subtle signatures in how the object's brightness changes over time. Natural comets typically brighten predictably as they approach the sun, their behavior following patterns we understand through decades of observation, with variations corresponding to rotation periods, surface heterogeneity, and outgassing patterns that respond to solar heating. An artificial object might display brightness variations following different rules, perhaps indicating controlled orientation changes or the operation of active systems that modulate reflected sunlight in ways that transcend natural tumbling and sublimation. Yet 3I Atlas's light curve corresponds to patterns astronomers observe in other comets, natural variations consistent with an irregular body rotating as it travels, responding to solar influence, exactly as physics predicts natural ice and rock should respond. So far, then, none of these artificial signatures have manifested. Radio silence persists. Trajectory remains purely gravitational. Brightness variations suggest natural rotation and surface features rather than controlled systems. The carbon dioxide dominance that makes 3I Atlas chemically unusual doesn't by itself suggest artificial origin, as we explored in Part 3 when examining natural processes that could produce CO2-rich compositions through radiation processing formation near specific snow lines or insulating dust mantles. Jumping from chemically unusual to artificially constructed would require evidence that none of these natural processes could account for observations, evidence that remains absent despite careful scrutiny. This is where lessons from Oumuamua become particularly relevant and instructive. That first confirmed interstellar visitor sparked intense speculation about possible artificial nature, driven partly by its unusual elongated shape and slight acceleration that initially seemed difficult to explain through natural processes. Radio telescopes conducted extensive searches for artificial signals, listening for any hint of technology, finding none. Detailed analysis of its motion revealed that outgassing from water, ice possibly from subsurface, reservoirs exposed by surface fracturing could account for observed non-gravitational forces. What initially seemed inexplicably exotic ultimately proved to have natural explanations, demonstrating how phenomena that challenge our experience can still operate within understood physics. Avi Loeb, that scientist who dares think differently, is like that friend who always asks, "But what if it's not what everyone assumes?" while the rest of the group has already reached consensus. Annoying sometimes, necessary, occasionally absolutely right. Science needs voices willing to question comfortable conclusions, even when most evidence supports conventional interpretations, because that's how paradigm shifts begin. Searching for radio signals from 3I Atlas feels like calling your crush. You hope for a response, prepare for multiple scenarios, rehearse what you'll say if they actually pick up, but ultimately, you just hear ringing that hollow tone of unanswered expectation echoing through the void. Occam's razor, the principle that simpler explanations are usually correct, is like hearing a noise at 3 a.m. Could be an intruder breaking in, dramatic and terrifying, but usually just the cat knocking over a glass. Boring but true, mundane but accurate, natural comet. That's the cat, alien probe. That's the intruder we imagine. When primitive fear circuits activate, and here we reach the end of Act 1, the conclusion of our careful journey through 3I Atlas's discovery properties, chemistry, safety assessment, and the fragile boundary between natural and artificial explanations. If you're listening to help sleep find you, this is a good moment to let your eyes close, to let tension drain from shoulders and jaw. We've covered what matters most. 3I Atlas is safe, beautiful in its strangeness, and teaching us about the universe beyond our small corner of space. Act 2 will venture deeper into bold speculation, into scenarios that push imagination to its limits while maintaining clear distinctions between what we observe and what we wonder. But for now, breathe deeply, release the day's concerns, let cosmic numbers lull you toward rest. 270 million kilometers distant, 5 billion years old, safe, absolutely mathematically, certainly safe. The universe is vast and strange and full of wonders, but this particular wonder passes harmlessly through our neighborhood, a messenger from ancient times, carrying lessons we're only beginning to understand, leaving us with questions that will echo long after it disappears back into the darkness between stars, where it wandered alone for longer than our sun has burned. Now, we venture into the deepest realm of speculative territory, where the shadows of cosmic possibility stretch towards scenarios that would fundamentally alter our understanding of our place in the universe, where comfortable assumptions about benign cosmic neighbors give way to darker interpretations of the great silence that surrounds us. What follows is pure thought experiment, a mental journey into implications and possibilities that current evidence does not support, yet which illustrate profound questions that could emerge if our assumptions about Three-Eye Atlas prove inadequate, if the natural explanation we've carefully constructed begins to show cracks that widen into chasms of uncertainty. The dark forest hypothesis emerges from both science fiction and serious city discourse, drawing its name from Liu Cixin's acclaimed novel, but representing a genuine philosophical position about the nature of cosmic civilization that demands our attention not because it's necessarily correct, but because it forces us to confront uncomfortable possibilities about why the universe appears so empty, despite offering countless opportunities for life to arise and intelligence to flourish. The idea suggests that advanced civilizations might remain deliberately hidden from one another, operating under the assumption that revealing one's existence and capabilities could invite predation from even more advanced neighbors whose intentions remain unknowable until contact occurs. And by then, it might be catastrophically too late to reverse course or mount effective defense. In such a universe, silence becomes a survival strategy refined across millions of years of evolution, a hard lesson learned by countless civilizations that made the fatal mistake of broadcasting their presence before understanding the true nature of the cosmic neighborhood they inhabited. The core reasoning carries brutal logic that's difficult to dismiss entirely. The space between stars is so vast, the information propagation so slow, that you cannot possibly know who's listening or what their intentions might be until signals have already traveled light years in all directions, advertising your location, your technology level, your potential vulnerabilities to any intelligence sophisticated enough to detect and interpret those transmissions. Therefore, the safest choice becomes silence observation, without revelation, never exposing your position or capabilities until you've thoroughly mapped the cosmic terrain and identified potential threats or allies with certainty that our current technology cannot provide. If we allow ourselves to imagine, and we stress this, remains pure imagination, unsupported by any observational evidence, that Three-Eye Atlas represents not a natural comet, but some form of reconnaissance probe, the implications would stagger even the most prepared minds. Such a scenario would suggest our solar system is being surveyed by intelligences capable of engineering objects that can survive billion-year journeys between stars while remaining virtually indistinguishable from natural phenomena, mimicking cometary behavior so perfectly that only the most subtle anomalies might betray their true nature. The very perfection of such disguise would indicate a level of technological sophistication that dwarfs our current capabilities. By margins, we struggle to conceptualize, suggesting mastery not just of propulsion and material science, but of deception of understanding natural processes so thoroughly that artificial constructs become indistinguishable from genuine geological specimens shaped by time and cosmic forces rather than intelligent design. Consider the engineering requirements. Such a scenario would demand the technical challenges that would need solving before any civilization could deploy camouflaged surveillance assets across interstellar distances. A probe designed to pass for a comet would need to mimic every aspect of natural cometary behavior with precision that defeats our most sophisticated instruments. The correct spectroscopic signatures, matching natural ice and rock compositions, appropriate outgassing patterns that respond realistically to solar heating rather than following programmed schedules that might reveal artificial control surface properties that reflect and absorb light in ways consistent with natural materials. Weathered by billions of years in interstellar space, it would need to carry sufficient volatile materials to maintain its disguise throughout passage through our solar system, generating the characteristic coma we expect from sublimating ices, while simultaneously housing whatever sensors, processors, and communication systems would justify such an elaborate mission across the vast darkness between stars, where nothing happens for millions of years until suddenly a solar system appears and observation windows open for mere months before the probe rushes past and continues into the void. The power requirements alone would be formidable, demanding energy sources that remain functional across time scales that make human civilization look like a brief spark. Maintaining active systems across interstellar distances and billion-year timescales would demand either radioisotope thermoelectric generators using exotic isotopes with half-lives measured in geological epochs, or perhaps advanced fusion reactors that operate on trace interstellar hydrogen harvested during the long journey between stars, or maybe even more exotic mechanisms like cosmic ray energy harvesting or magnetic field interactions that we haven't yet discovered or learned to exploit. But let's push this speculative scenario to its dramatic conclusion, following the logic wherever it leads, even knowing we're venturing far beyond what evidence supports. Imagine that our continued observation of 3I Atlas begins to reveal anomalies that cannot be explained by natural processes, subtle deviations that accumulate until the natural explanation becomes untenable. And we're forced to confront possibilities we'd prefer to dismiss. Perhaps radio telescopes detect brief structured transmissions as the object passes through the outer solar system signals, too organized to arise from random processes, displaying modulation patterns that suggest information encoding or coordinate transmission. Maybe its trajectory shows minute but unmistakable course corrections that suggest active guidance rather than purely ballistic motion governed by gravity and initial velocity. Or possibly Its chemical emissions display patterns too complex and organized to result from random sublimation molecular ratios that shift in ways suggesting controlled release rather than passive response to solar heating. The trigger moment in this speculative narrative might arrive when 3i Atlas begins to deploy secondary objects, smaller probes that separate from the main body and take up positions throughout our solar system, like seeds planted in prepared soil. One might establish orbit around Venus, studying the hellish greenhouse conditions that demonstrate what happens when planetary climate systems spiral out of control. Another, around Mars, examining a world that once held liquid water and possibly life before losing its atmosphere to solar wind and magnetic field collapse. Others scattered through the asteroid belt or positioned at gravitationally stable Lagrange points where they can observe indefinitely with minimal fuel expenditure, creating a surveillance network of unknown origin and capability that suddenly occupies our cosmic neighborhood. Suddenly, our solar system would host a surveillance network whose purposes remain opaque, whose creators remain unknown, whose capabilities exceed anything we can currently imagine or counter. The question that would immediately arise, echoing through halls of power and scientific institutions worldwide, how should humanity respond? This hypothetical scenario would instantly become the greatest diplomatic and strategic challenge our species has ever faced, dwarfing Cold War tensions and ideological conflicts that at least involved adversaries we could see, understand, and negotiate with, according to shared evolutionary psychology and common terrestrial experience. Unlike the gradual first contact scenarios, often depicted in science fiction, where decades of radio communication might precede physical encounter and allow for mutual understanding to develop slowly through careful dialogue, the discovery of an active surveillance network would confront us with the reality of technologically superior intelligence already operating in our immediate cosmic neighborhood, already gathering data, already making assessments according to criteria we cannot fathom. The governance questions would be unprecedented and urgent, demanding answers to problems no political theory or international relations framework has adequately addressed. Who has the authority to speak for Earth when addressing entities whose existence transcends our planetary boundaries and political divisions? The United Nations, designed for coordinating terrestrial nation-states rather than representing humanity to cosmic civilizations. The major space agencies like NASA, ESA, or CNSA, which possess technical expertise but lack diplomatic mandates, individual nations with advanced space capabilities acting unilaterally according to perceived national interests that might conflict with species-level survival, or the scientific community that made the discovery, who understand the technical details but lack authority to commit humanity to binding agreements or strategic responses. The complexity of achieving global consensus on something so momentous staggers the imagination, particularly given our species' track record of cooperation on far simpler challenges like climate change, pandemic response, or nuclear weapons proliferation, issues where stakes are enormous yet still comprehensible within frameworks of terrestrial politics and national interest rather than species survival in a potentially hostile cosmos. The active SETI debate would suddenly shift from theoretical discussion to immediate practical concern, requiring urgent policy decisions with civilizational implications. The SETI community has long debated the wisdom of transmitting signals into space versus merely listening for signals from other civilizations, with some arguing that advertising our presence could attract unwanted attention from potentially hostile aliens, while others contend that remaining silent while conducting increasingly sophisticated astronomical observations provides no real protection, since any civilization capable of interstellar travel would likely detect our technological signatures, regardless of our transmission policies. Reading our presence in the atmospheric composition, changes caused by industrial activity, the electromagnetic leakage from radio and television, broadcasts the infrared signatures of our cities, and the geometric patterns of our agriculture visible from space. But in our speculative scenario, the choice might be taken from us entirely, the decision made by the discovery itself, rather than by careful deliberation among policymakers and scientists weighing risks and benefits. If 3i Atlas and its hypothetical secondary probes were actively studying human civilization, our response itself would become part of the data being collected, observed, and analyzed by whatever intelligence deployed these assets across interstellar distances. Silence might be interpreted as wisdom, or fear, calculated caution, or paralyzing terror. Attempts at communication might suggest aggression or curiosity, hostile intent, or naive openness. Even the internal debates about how to respond would reveal fundamental aspects of human nature and social organization to whatever intelligence was monitoring us, exposing our political divisions, our technological limitations, our philosophical uncertainties about our place in the cosmos, and our readiness or unreadiness for contact with intelligences that might view us as we view insects, or perhaps as equals worthy of dialogue. Think about it. The dark forest makes you consider that moment when you're alone in an elevator with a stranger, both silent, neither daring to speak. First, primitive social calculus, weighing risk and reward of engagement. Now multiply that awkwardness by galactic scale, where speaking first might mean extinction, and you begin to understand the brutal logic that could keep the cosmos quiet, despite being populated by countless civilizations, all hiding in the darkness, all afraid to reveal themselves. An automated system 1 billion years old, still functioning perfectly. My iPhone dies after 2 years despite expensive engineering and planned obsolescence that ensures replacement purchases. If aliens actually possess technology that outlasts stellar lifetimes, honestly, I just want them to design smartphone batteries. The engineering alone would revolutionize terrestrial industry, even if they never share anything else. That's the dark forest. In its darkest interpretation, a cosmos full of life, all hiding, all afraid. Heavy, isn't it? Let's take a breath here. The universe we're describing is speculative. Remember, pure thought experiment. But it raises a question that haunts every SETI scientist during quiet moments. If the dark forest is real, if civilizations routinely hide until they die, what kills them? What filter catches nearly everyone? Let's explore that next, though perhaps the answer is even more unsettling than the silence itself. The concept of the Great Filter emerges from one of the most profound questions facing any technological civilization, a puzzle that becomes more pressing with each year that passes without detecting signals from the stars or encountering evidence of intelligence beyond our own. If the universe should be teeming with intelligent life, given the vast numbers of planets, the billions of years available for evolution, and the apparent ease with which life arose on Earth shortly after conditions became suitable, then why do we see no evidence of cosmic neighbors, despite decades of increasingly sophisticated searches? This philosophical puzzle, first articulated by physicist Enrico Fermi during a casual lunch conversation in 1950, with a question so simple, it cuts to the heart of cosmic existence. Where is everybody? Has spawned decades of speculation about barriers that might prevent life from arising, evolving intelligence, or surviving long enough to spread throughout the galaxy and make its presence unmistakable to observers like ourselves who scan the heavens with ever-improving instruments, yet find only silence where we expected a cacophony of voices calling across the darkness. The Great Filter hypothesis suggests that somewhere in the long chain of evolutionary development, from simple chemistry to spacefaring civilization capable of making its mark on the cosmic stage, there exists a step so improbable, so difficult, or so dangerous that virtually all attempts to pass through it result in failure, extinction, or transformation into something unrecognizable. This filter could occur early in the process, perhaps in the transition from non-living matter to self-replicating systems, that mysterious step where chemistry becomes biology and inert molecules begin the long climb toward complexity and awareness. If this early filter is the answer, then life itself might be extraordinarily rare, a cosmic lottery, one so infrequently that intelligence arises only once per galaxy, or perhaps once per observable universe, making us not just alone, but profoundly, terrifyingly unique. Alternatively, the filter might emerge later, when civilizations develop technologies powerful enough to destroy themselves faster than they can learn to use them wisely, when the same capabilities that enable interstellar communication and space exploration also provide means for total annihilation through nuclear weapons, runaway artificial intelligence, nanotechnology accidents, or climate disruption that renders planets uninhabitable. In our speculative exploration of 3i Atlas, we must confront the possibility that this ancient wanderer might carry messages from intelligences that encountered their own insurmountable barriers, civilizations that solved the technical challenges of interstellar probe construction, but ultimately succumbed to forces that technology alone could not overcome. If this object represented engineered technology rather than natural phenomena, and we must constantly repeat that no evidence supports this interpretation, the fate of its creators becomes a question of paramount importance, a mystery that connects our speculation about this particular object to the broader question of why the universe appears so empty, despite offering countless opportunities for intelligence to arise and flourish. The object's apparent age, potentially billions of years, based on its thick disk galactic origins, places its hypothetical construction in the deep history of our galaxy, when stellar populations, chemical abundances, and cosmic conditions differed substantially from those we observe today, when the universe was younger and perhaps more violent, when different laws might have governed the probability of technological civilization arising and surviving. If this ancient visitor were indeed artificial, a product of deliberate engineering rather than natural geological processes, did the civilization that created it survive long enough to see it reach our solar system to receive the data it might transmit back across light years of space to learn what it discovered about the descendants' stellar neighborhoods that existed when they first launched their probe into the darkness? The timescales involved become almost incomprehensible when examined carefully, straining our ability to think across geological epochs rather than human lifespans, or even civilizational timespans measured in thousands rather than billions of years. Human civilization, from the first agricultural settlements to our current space age, spans roughly 10,000 years, a period that seems vast from our perspective, yet represents merely a blink in cosmic time. Recorded history covers perhaps 5,000 years, the written record we can examine to understand how we became what we are. Our technological civilization, the period during which we've possessed capabilities that might be detectable from interstellar distances, has existed for mere centuries, a few hundred years at most, since the Industrial Revolution began transforming our species' relationship with energy and materials. Yet 3i Atlas, if artificial, would represent technology that has been operational for millions of times longer than our entire civilizational history, a span so vast that comparing it to human timescales becomes an exercise in futility, like comparing a single heartbeat to geological epochs that measure continental drift and mountain building. This raises profound questions about technological longevity versus biological survival, about whether the artifacts of intelligence might long outlast their creators, whether the cosmos might be littered with ancient probes that persist long after the civilizations that launched them have vanished from the galaxy, leaving behind only these messenger bottles floating through the cosmic ocean, carrying information from minds that solved interstellar communication challenges, but ultimately failed to solve the deeper challenge of long-term survival in a universe that may be fundamentally hostile to persistent technological civilization. Perhaps the most haunting possibility is that we might be encountering probes that persist long after their makers have vanished, cosmic messages in bottles floating through the galaxy, carrying information from civilizations that solved the technical challenges of interstellar communication and probe construction, but ultimately succumbed to other forms of the great filter barriers that technological sophistication alone could not overcome. Consider the engineering implications of creating technology that remains functional across such timescales, requirements that dwarf anything humanity has ever attempted or seriously contemplated. Our most durable human artifacts, the pyramids of Egypt, ancient stone monuments like Stonehenge, certain radioactive isotopes we've created operate on timescales of thousands to millions of years, already impressive by terrestrial standards, but trivial compared to the billion-year operational lifetime we're discussing for hypothetical interstellar probes. Maintaining complex electronic systems, propulsion mechanisms, and artificial intelligence across billions of years would require engineering principles we can barely imagine. Material science that produces components more durable than diamond, yet flexible enough to self-repair when damaged, energy systems that remain operational longer than most stars, burn software architectures that can adapt and self-repair across geological time without succumbing to bit rot or accumulating errors that corrupt core programming. The success of such engineering would paradoxically suggest that its creators possessed extraordinary technological capabilities, mastery of physics and materials that we're only beginning to understand in our most advanced laboratories. Any civilization capable of launching billion-year interstellar missions would have solved numerous technical challenges that we haven't even begun to address, seriously understanding materials at the atomic level well enough to design structures that resist radiation damage and micrometeorite impacts across eons, generating and storing energy at cosmic scales efficiently enough that power remains available after journeys measured in galactic rotation, periods processing information across deep time without data degradation or system failures that would render the probe useless long before reaching its destination. Such capabilities would seem to offer protection against many potential great filter scenarios, suggesting wisdom and technical sophistication that should enable long-term survival. Yet if 3i Atlas were indeed their creation, and if it remains the only evidence we observe of their existence, despite their apparent technological prowess, what great filter might have claimed them, despite capabilities that dwarf our own? The possibilities are sobering to contemplate and multiply rapidly once we begin considering the various ways that advanced civilizations might fail. Perhaps they fell victim to resource depletion on a galactic scale, expanding so rapidly that they consumed the energy and materials necessary for their civilization's survival faster than they could find or develop alternatives, like a cancer that grows too successfully and kills its host through metabolic exhaustion. Maybe they encountered other intelligences that proved hostile, triggering conflicts that destroyed both aggressor and defender in mutual annihilation that left no survivors to continue either civilization's legacy. More unsettling still, they might have succumbed to internal contradictions inherent in advanced technological civilization, where the same capabilities that allowed them to engineer interstellar probes also enabled forms of a warfare, environmental destruction, or social collapse that proved impossible to control once initiated. History offers numerous examples of civilizations that developed technologies more rapidly than the wisdom to use them safely, from ancient societies that deforested their lands and collapsed through agricultural failure, to our own ongoing struggles with nuclear weapons, climate change, and artificial intelligence development, where capability races ahead of control and understanding races behind implementation. Or perhaps the great filter involves not catastrophic destruction, but evolutionary transcendence, transformation so complete that the resulting entities no longer resemble their biological ancestors or maintain interest in the physical universe that spawned them. Perhaps sufficiently advanced civilizations inevitably transform themselves in ways that render them unrecognizable or undetectable to emerging species like ourselves, uploading consciousness into quantum computing systems that operate on timescales and dimensions we cannot perceive, merging with their technology so completely that the distinction between intelligence and artifact disappears entirely, or ascending to higher dimensions of existence that remain invisible to our current instruments and conceptual frameworks, limited by evolution in 3 spatial dimensions and forward time. The Great Filter serves as both warning and inspiration, a concept that should inform our approach to our own technological development and long-term survival strategies. It warns that technological capability alone may not guarantee survival, that advancement brings new forms of risk as well as opportunity, that we must be thoughtful about how we develop and deploy powerful technologies whose consequences we may not fully understand until after deployment, when reversing course becomes impossible. But it also inspires us to think carefully about how we manage our own development, how we balance exploration with wisdom, how we might design solutions that prove more durable than the civilizations that create them, building in redundancy and safety margins that account for unknown risks and unintended consequences. The Great Filter is like the ultimate final exam every civilization must pass. Where is humanity now? We've passed the midterms, surviving the Stone Age, avoiding extinction from ice ages and volcanic eruptions. We're currently working on our major projects: nuclear energy without nuclear war, artificial intelligence without losing control, climate stability without environmental collapse. The final exam, still ahead, still unknown, still waiting to test whether we possess the wisdom to match our growing capabilities. Technology that functions for 1 billion years. Meanwhile, my laptop needs rebooting after every Windows update, freezing at crucial moments and losing unsaved work with gleeful regularity. Clearly, any aliens capable of billion-year engineering didn't use Windows, or perhaps they solved the software reliability problem along with fusion power and faster-than-light travel advances that seem equally miraculous from our current perspective. That's the Great Filter laid bare the idea that getting from single cells to starfaring civilizations is so hard that almost no one makes it, and those who do might not last long enough to matter. It's sobering. It's also, in a strange way, motivating. Because if the filter exists, if civilizations routinely fail at certain stages, then understanding where it lies becomes crucial for our own survival. Maybe we've already passed it. Maybe it's still ahead. Maybe 3i Atlas, whether natural or artificial, is evidence that someone else passed through, and what they left behind outlasted them by eons. Either way, it's a reminder that existence at cosmic scales is precarious, that intelligence is precious, that every night we look up at stars that might have once hosted civilizations that ask the same questions we're asking now, and found answers we're still searching for, or perhaps never found answers at all before the silence claimed them too. The question echoes through every astronomical discovery, lurking behind every search for extraterrestrial intelligence, haunting every moment when we peer into the cosmic dark and find only silence where we hoped for conversation, only emptiness where we expected bustling neighborhoods of civilizations at various stages of development calling out across the void. Enrico Fermi posed it during a casual lunch conversation in 1950, a simple inquiry that has only grown more profound as our understanding of the universe has expanded and our instruments have become more sensitive, yet still detect no unambiguous signs of technological civilizations beyond our own. Where is everybody? The Fermi paradox takes on new dimensions when we consider interstellar objects like 3I Atlas, each visitor from beyond our solar system representing a natural experiment in the distribution of matter throughout the galaxy, a sample of materials and processes that occur around other stars in stellar neighborhoods we've never visited and may never reach with physical spacecraft. In principle, these wandering ambassadors should eventually reveal signatures of technological civilization if such civilizations exist in any abundance engineered materials, with isotope ratios that couldn't arise naturally artificial structures that betray intelligent design through geometric patterns or functional organization, perhaps even active systems still operating after their long journey through the darkness between stars. Yet so far, all confirmed interstellar visitors have appeared thoroughly natural, displaying characteristics we can explain through geological and chemical processes that require no intelligence to produce only time and the fundamental forces that shape matter across cosmic distances and timescales. Oumuamua, despite its unusual, elongated shape and slight acceleration that initially seemed difficult to explain, ultimately revealed itself as natural through careful analysis that showed how outgassing from subsurface ice could account for observed non-gravitational forces. 2I Borisov displayed classic cometary behavior throughout its passage, behaving exactly as physics predicted. A natural icy body should behave when exposed to solar heating. 3I Atlas, for all its chemical peculiarities and extreme velocity, shows every sign of being natural rather than artificial. Its CO2-rich composition, explainable through natural formation processes around different types of stars or radiation processing over billions of years in interstellar space. This absence might be telling us something profound about the nature of advanced civilization and its relationship to interstellar space, about whether technology leaves lasting marks on cosmic debris, or whether civilizations capable of interstellar engineering choose to remain hidden, or perhaps don't exist in the abundance we once hoped. Perhaps truly advanced societies prefer what we might call silent emissaries, surveillance assets designed to be indistinguishable from natural phenomena, if they send probes at all, rather than simply listening passively for signals from younger civilizations. In such a scenario, the very sophistication of alien technology would render it invisible to our current detection methods, which remain calibrated to recognize, obviously, artificial signatures, like radio transmissions or geometric structures, rather than subtle deviations from natural behavior that might indicate controlled systems operating according to principles we haven't discovered. But this raises immediate questions about what those signatures would actually look like In practice, how we would recognize artificial intelligence if it's specifically designed to avoid recognition, what observational evidence would ultimately reveal true nature, despite elaborate camouflage that mimics natural processes with precision our instruments cannot penetrate? The answer returns us to fundamental distinctions between natural and artificial phenomena in space boundaries that may prove more subtle and complex than our current understanding suggests lines that blur when intelligence becomes sophisticated enough to mimic nature perfectly. Narrowband radio emissions would represent the most obvious technological signature, standing out clearly against the broadband noise that natural processes produce energy concentrated in narrow spectral lines that couldn't arise from thermal radiation or plasma interactions, but only from deliberate transmission by devices designed to communicate across interstellar distances. The search for extraterrestrial intelligence has focused on detecting exactly such signals for decades, operating under the assumption that any civilization capable of interstellar communication would produce detectable electromagnetic signatures, either intentionally through beacon transmissions or accidentally through leakage from internal communications and power generation systems. So far, 3i Atlas has remained radio silent, emitting only the natural electromagnetic signatures expected from sublimating cometary material interacting with the solar wind and magnetic fields, producing plasma emissions that follow understood physics rather than displaying modulation or structure that would betray artificial control. Unnatural thermal profiles might provide another diagnostic tool for distinguishing artificial from natural objects, subtle signatures in how heat distributes across surfaces or radiates into space. Natural objects achieve thermal equilibrium with their environment according to well-understood physical principles. They absorb solar radiation at rates determined by their surface properties, re-radiate energy in the infrared spectrum according to their temperature and emissivity, and maintain surface temperatures determined by the balance between absorbed and emitted energy, modified by internal heat sources like radioactive decay. Artificial objects might display temperature distributions that violate these natural patterns through internal heat generation from power systems, asymmetric heating that suggests active thermal management, or thermal signatures that change in ways inconsistent with passive response to solar influence. Current infrared observations of 3i Atlas show thermal signatures consistent with solar heating of natural cometary materials, surface temperatures rising as it approaches the sun, following the inverse square law that governs solar energy distribution, with spatial distribution of heat across its surface appearing random and shaped by topographic features and compositional variations, rather than designed thermal management systems that would indicate deliberate temperature control. Controlled maneuvers would represent perhaps the most definitive evidence of artificial origin, unambiguous proof that we're dealing with technology rather than geology. Natural objects in space follow trajectories determined solely by gravitational forces and the occasional thrust provided by outgassing materials as ices sublimate and expand into vacuum, creating rocket effects in miniature that slightly alter orbital paths. These non-gravitational accelerations are typically small, random, indirection, or at least unpredictable in ways that correlate with surface features and rotation rather than mission objectives, and closely correlated with measures of cometary activity like coma brightness and gas production rates that track solar heating patterns. Artificial probes, by contrast, might display controlled course corrections executed at optimal times to achieve specific trajectory goals. Intentional velocity changes that cannot be explained by passive outgassing or trajectory modifications that serve identifiable purposes like establishing particular observation geometries or avoiding hazards that natural objects would encounter without deviation. Such maneuvers would need to be carefully distinguished from the chaotic forces produced by asymmetric outgassing, which can create thrust vectors that change unpredictably as different surface regions become active or as rotation exposes fresh ices to sunlight, but persistent patterns of controlled motion would eventually become apparent through precise astrometric measurements that track position with sufficient accuracy to detect deviations from purely gravitational trajectories. 3i Atlas has shown no signs of controlled maneuvers throughout our observations, its trajectory following the smooth hyperbolic arc predicted by gravitational calculations, with only minor perturbations that correspond exactly to expected effects of solar radiation pressure and outgassing forces, natural accelerations that require no intelligence to explain, and indeed would be puzzling if absent from an object showing clear signs of cometary activity through its carbon dioxide coma. The natural explanation for interstellar objects, like 3i Atlas, aligns well with theoretical expectations about planetary system formation based on computer simulations that model the early violent history of stellar systems. These simulations suggest that all stellar systems should eject substantial quantities of rocky and icy debris during their early evolution. When massive planets migrate and gravitational interactions scatter smaller bodies into chaotic orbits, some falling into the star, others ejected into interstellar space at velocities that exceed escape velocity and commit them to eternal wandering. The galaxy should be filled with such nomads, planetesimals that began forming around other stars but were flung into the void before they could accrete into full-fledged worlds, carrying with them chemical signatures of their birth environments and mechanical memories of the violence that liberated them from their home systems. From this perspective, the steady trickle of interstellar visitors we've begun detecting represents exactly what astronomical theory predicts natural consequences of planetary formation operating according to understood gravitational dynamics rather than deliberate deployment of artificial probes. Oumuamua, 2i Borisov, and 3i Atlas are the leading edge of a much larger population that future surveys will reveal as our instruments improve and our observation campaigns become more systematic, transforming interstellar objects from rare curiosities that make headlines into routine astronomical phenomena that we catalog and study as naturally as we observe asteroids or comets from our own solar system. The Vera Rubin Observatory, scheduled to begin operations later this decade, should detect interstellar objects at rates of several per year once its wide-field survey reaches full operational capacity, providing statistical samples large enough to test theoretical predictions about origins, compositions, and trajectories rather than relying on tiny samples dominated by selection effects and observation biases. This statistical argument provides one possible resolution to the Fermi paradox's application to interstellar objects, explaining the absence of obvious artificial signatures without invoking elaborate concealment strategies or pessimistic conclusions about the rarity of technological civilization. If natural ejected planetesimals greatly outnumber any artificial probes that might exist, then the artificial signatures we seek might be hidden in a background of natural wanderers, like needles in cosmic haystacks of impossible size. Detecting alien technology would require distinguishing a few engineered objects from thousands or millions of natural ones, identifying subtle anomalies that betray artificial origin despite sophisticated camouflage, or simply recognizing patterns that emerge only when sample sizes grow large enough to reveal statistical deviations from natural distributions. The Fermi paradox feels like arriving at a party. The house is huge, music's playing, food's laid out on tables, but nobody's there. You stand in the doorway, wondering, am I too early, too late? Or did I get the wrong address entirely? That's humanity's situation. With the galaxy, we showed up expecting neighbors and found empty rooms echoing with our own questions. Searching for alien technology among millions of natural objects is like trying to find a dropped iPhone in the Amazon rainforest. Technically possible? Yes. Practically feasible? Well, good luck distinguishing your smartphone from the roughly iPhone-shaped rocks, seed pods, and tree bark that litter the forest floor. At least in the rainforest, you could turn it on and listen for the vibration. In space, alien probes might stay silent forever. So here we are, 3 interstellar visitors, 3 natural explanations. The galaxy might be full of life that hides so well we'll never see it, or perhaps it's full of rocks and ice and nothing else. Either possibility is profound. Either answer changes everything. But there's one more scenario to consider before we leave this speculative territory, one that ventures into the realm of pure science fiction while maintaining just enough connection to physics to fuel nightmares or dreams depending on your perspective. What if the invasion already happened and we just didn't notice because it came microscopic, patient, and impossibly subtle? Let's explore that darkness next. Now, we descend into the realm of pure cinematic speculation, where the boundary between plausible science fiction and observed reality blurs into scenarios that would challenge everything we think we know about life intelligence and the cosmos, where our instruments fall completely silent and we navigate only by imagination, guided loosely by physics and evolutionary logic, pushed to their absolute limits. What follows represents the outer edge of possibility, ideas so speculative that they require suspension of multiple scientific principles while still maintaining enough connection to known physics to fuel our speculation rather than descending into pure fantasy, disconnected from observable reality. Picture this scenario, however improbable. 3i Atlas isn't merely a probe or even a conventional spacecraft, but rather a delivery system for something far more insidious and sophisticated than bulk machinery or obvious artificial structures, something that could infiltrate our world so subtly that detection would require technologies we haven't invented and vigilance we haven't considered necessary, hidden within its icy matrix, microscopic devices, or perhaps even engineered biological entities. Let's call them microseeds. For convenience, lie dormant, awaiting activation by specific environmental triggers that might not occur for centuries or millennia after delivery, patient beyond human comprehension, designed to survive conditions that would destroy any technology we've ever built. These could be nanotechnological constructs designed to survive the harsh conditions of interstellar space. For billions of years, molecular machines built from exotic materials that resist radiation damage and maintain structural integrity across geological timescales. Or they might represent some form of pan-galactic life that spreads between star systems through exactly this mechanism, biological rather than mechanical, but engineered rather than evolved, designed specifically for interstellar dispersal and activation only, under conditions that indicate suitable targets for whatever purposes drive their dispersal across cosmic distances and timescales. The concept isn't entirely without precedent in scientific speculation, though it remains firmly in the realm of hypothesis rather than tested theory. The panspermia hypothesis, while controversial and far from proven, despite garnering attention from serious scientists, suggests that life itself might spread throughout the galaxy via comets, asteroids, and other interstellar wanderers that carry dormant microorganisms from world-to-world seeding planets with the building blocks, or even complete genetic systems that jumpstart biological evolution. Some researchers have proposed that hardy microorganisms could survive the radiation vacuum and extreme cold of space for millions or even billions of years, encased in protective rock or ice, remaining dormant until favorable conditions trigger reactivation and reproduction, allowing life to propagate across interstellar distances without requiring intelligent intervention or deliberate seeding missions. But our speculative scenario goes far beyond passive panspermia into the realm of directed dispersal, where the microseeds represent engineered systems designed not merely to survive interstellar transit, but to remain dormant until specific activation conditions are met. Conditions that might indicate the presence of suitable host environments or technological civilizations worth studying or influencing according to criteria established by whoever designed these microscopic ambassadors. These hypothetical microseeds would need to maintain structural integrity across billion-year timescales, while exposed to cosmic radiation that gradually destroys molecular structures, interstellar dust impacts that occur at relative velocities measured in kilometers per second, and the extreme temperature variations encountered during passage through the deep freeze of interstellar space and periodic warming during stellar flybys that might occur multiple times during their wandering before finally encountering our solar system. They would require power sources that remain functional longer than most stars burn, perhaps utilizing radioactive decay of exotic isotopes with half-lives measured in billions of years, or maybe harvesting energy from cosmic ray impacts or zero-point fluctuations in the quantum vacuum mechanisms that remain theoretical even by the standards of our most advanced physics. Information storage systems would need to avoid data degradation over geological time, perhaps encoding instructions in crystal lattices or quantum states that remain stable indefinitely, or using redundant storage with error correction codes sophisticated enough to reconstruct original information despite bit flips caused by radiation damage. Manufacturing capabilities would need to bootstrap complex technology from raw materials found on alien worlds, self-assembling into larger structures, when activated perhaps using principles of molecular nanotechnology or biological self-organization to build functional systems from nothing more than ambient atoms arranged according to encoded instructions. But if such technology were possible even hypothetically, the strategic implications would be terrifying in their scope and subtlety. A single interstellar object, like 3IR Atlas, could carry billions or trillions of microscopic seeds, each capable of establishing a foothold on any world it eventually reaches, dispersed so widely throughout the solar system during passage that some inevitably contact every planetary surface and moon in our neighborhood. The invasion, if we can call it that, without descending into paranoid fantasy, would be silent, patient, beyond human comprehension, and virtually undetectable until the activation phase began according to schedules or triggers established billions of years ago by intelligences that might no longer exist by the time their microseeds finally reach destinations and begin executing programmed instructions. The activation scenario in our speculative narrative might unfold centuries or millennia after 3I Atlas passes through our solar system, the seeds remaining dormant through generations of human civilization, perhaps even outlasting humanity entirely if activation conditions require technological or population thresholds we haven't yet reached. Perhaps the seeds are designed to trigger when Earth's technology reaches specific thresholds, detectable through electromagnetic emissions or atmospheric composition changes when we achieve interstellar travel ourselves, and thus demonstrate readiness for whatever contact or transformation the seeds are designed to facilitate when our population reaches certain levels that indicate stable global civilization, or when our industrial activity produces particular atmospheric signatures that mark us as suitable targets for whatever purposes drive their deployment across interstellar distances. This microseed scenario feels like worrying about dangerous bacteria on every doorknob technically possible, somewhat concerning, but usually just your anxiety talking rather than actual threat assessment. Should you wash your hands? Yes, basic hygiene. Should you panic about invisible invasions? Probably unnecessary unless evidence suggests otherwise. Technology that self-assembles from raw materials. IKEA hasn't managed that with furniture after 80 years of trying, and their instruction manuals allegedly come from Earth. If aliens solved that problem, along with interstellar travel, honestly, they've earned whatever they accomplish through sheer engineering competence that deserves admiration rather than resistance. We just walked through the most Hollywood scenario of this entire story: microscopic alien seeds lying dormant in cosmic debris, waiting to activate according to billion-year-old programming. It's wild. It's fun to imagine. It's also almost certainly not happening for reasons we'll explore shortly, involving radiation dilution and basic physics that make this scenario implausible, despite its cinematic appeal. But that's the point of speculation. Pushing imagination to its limits shows us the boundaries of possibility, helps us distinguish between legitimate concerns and paranoid fantasy, and maybe prepares us for genuine surprises that fall somewhere between boring rocks and invasion fleets. Now let's return to firmer ground and talk about how humanity actually responded to 3I Atlas with science cooperation and remarkable competence that offers hope for how we might handle even stranger discoveries in the future. We've wandered far into speculative shadows, haven't we? Dark forests and great filters, ancient probes and microscopic invasions. Heavy stuff for minds trying to find rest. But here's what matters. What we can hold on to with confidence, built on observation rather than imagination. 3I Atlas is real. It's safe. And the way humanity has responded to its arrival tells a more hopeful story than any dystopian speculation. So let's come back now. Back to what we know. Back to what we've done right. Back to the science that illuminates, rather than frightening, that reveals a universe strange enough without requiring aliens hiding in every shadow. Ready? Let's talk about how we actually handle cosmic visitors and what that says about our species at its best. The response to 3I Atlas has been quite simply a testament to the best aspects of human scientific collaboration, a choreographed dance of telescopes, institutions, and individual researchers working together to extract maximum knowledge from a fleeting opportunity that will never repeat in any of our lifetimes. Within hours of the initial discovery by the Atlas survey on July the 1st, 2025, a global network of observatories had swung into coordinated action, demonstrating how modern astronomy operates as a truly international enterprise that transcends political boundaries and national interests in pursuit of knowledge that belongs to all humanity rather than individual nations or institutions. The immediate response followed protocols developed over decades of asteroid and comet discovery, refined through experience, with thousands of solar system objects, and now applied seamlessly to this visitor from interstellar space. The Minor Planet Center at the Harvard-Smithsonian Astrophysical Observatory served as the central clearinghouse for astrometric observations, collecting position measurements from observatories worldwide and refining the object's orbital elements, with each new data point updating predictions about its trajectory and closest approach distances as observations accumulated and uncertainties shrank. The European Space Agency's Space Situational Awareness Program added its own tracking capabilities, contributing independent orbital calculations that confirmed NASA's assessments and provided redundancy that eliminated single-point failures in our understanding. NASA's Planetary Defense Coordination Office evaluated any potential Earth impact risk through calculations that quickly ruled out collision scenarios, determining with mathematical certainty that 3I Atlas posed no threat to our world or any other planet in our solar system, despite its tremendous velocity and hyperbolic trajectory that marked it as definitively interstellar in origin. But 3i Atlas's interstellar nature elevated the response beyond routine asteroid tracking procedures into a coordinated campaign of scientific observation unprecedented in its scope and urgency. The Hubble Space Telescope received priority target of opportunity scheduling, interrupting previously planned observations to image this unprecedented visitor during the brief window when it remained within range of our instruments and bright enough for detailed study. The James Webb Space Telescope followed suit, dedicating precious observing time normally allocated months in advance to spectroscopic analysis of the object's unusual carbon dioxide-dominated coma, capturing molecular fingerprints that will fuel research papers for years to come and expand our understanding of chemistry in stellar environments we've never directly sampled. Ground-based observatories, from Chile's Atacama Desert to Hawaii's Mauna Kea, contributed complementary observations across the electromagnetic spectrum. Amateur astronomers with modest equipment, capturing images that complement professional data. Radio telescopes listening for artificial signals that might betray technological origin. Infrared instruments mapping thermal signatures that reveal surface properties and compositional variations. This coordinated response illustrates how the astronomical community has evolved to handle rapid response scenarios where opportunities are fleeting and collaboration is essential. Unlike the early days of astronomy, when discoveries might remain hidden in individual researchers' notebooks for months or years before publication, modern astronomical surveys automatically share their findings through established networks that notify researchers worldwide within minutes of detection. The information flow surrounding 3i Atlas has been remarkably transparent, demonstrating institutional commitment to public engagement and scientific openness that builds trust and maintains legitimate interest. NASA's official website provides regular updates on observational results, complete with detailed technical information for specialists and accessible explanations for general audiences who want to understand what we're learning and why it matters. The European Space Agency has published similar updates, emphasizing the collaborative nature of the observation campaign, highlighting contributions from institutions across continents and celebrating the international character of astronomical research that unites rather than divides. Popular astronomy publications like Sky and Telescope magazine have provided detailed technical coverage alongside practical observing guides for amateur astronomers, hoping to glimpse this interstellar visitor through their own telescopes. Though magnitude 11, brightness means only experienced observers with good equipment and dark skies have any chance of detection. The transparency extends to data archiving. Hubble and Webb observations are made available through standard astronomical archives, like the Mikulski Archive for space telescopes, allowing researchers worldwide to analyze the same data sets and verify each other's conclusions, ensuring that interpretations are tested against independent analysis rather than relying solely on initial assessments from discovery teams. But imagine if our speculative scenarios from earlier proved accurate, if future observations began revealing signatures that couldn't be explained through natural processes alone, coherent radio transmissions, controlled trajectory adjustments, or deployment of secondary objects throughout our solar system. How would our institutions and procedures scale up to handle what might become the most significant discovery in human history? The existing framework provides some guidance, though admittedly developed for scenarios less dramatic than confirmed alien technology. The International Astronomical Union has protocols for verifying extraordinary claims requiring independent confirmation from multiple observatories before accepting results that challenge established scientific understanding. The SETI Institute has developed communication protocols for potential first contact scenarios, including guidelines for information sharing, public notification, and international cooperation that attempt to ensure coordinated response rather than competitive chaos. Space agencies have planetary protection procedures designed to prevent contamination of Earth by alien microorganisms or theoretically more exotic forms of life. Protocols involving strict containment analysis in specialized biosafety laboratories and careful evaluation of any biological or technological signatures before making definitive announcements. Yet none of these existing frameworks were designed to handle the discovery of active alien technology operating within our solar system surveillance networks or probe deployments that would represent intelligence not just capable of interstellar travel, but currently present and observing. The scale of coordination required would dwarf anything previously attempted in scientific research, raising questions of jurisdiction and authority that no international treaty adequately addresses. This response to 3i Atlas has been like watching a group project actually work, rare in human experience, but beautiful when it happens. Institutions sharing data, researchers collaborating across borders, transparency winning over secrecy. It's enough to restore some faith in our species' ability to handle the genuinely unprecedented without descending into competitive chaos or paranoid secrecy that serves no one. Scientists are sharing data faster than teenagers, share memes on social media, which honestly seems impossible given typical academic publication timelines where discoveries can remain locked behind paywalls for months or years. The fact that Hubble and Webb observations became publicly available within weeks of acquisition suggests we can cooperate when we want to, when stakes are high enough to overcome institutional inertia and competitive pressures that normally slow knowledge dissemination to frustrating crawls. The journey that brought 3i Atlas to our cosmic doorstep spans distances and timescales that challenge human comprehension, yet understanding these scales is crucial for grasping both the object's significance and our own place in the vast theater of galactic evolution that operates according to time frames that dwarf civilizational history. When we speak of thick disk galactic origins, we're invoking a story that began when the universe was less than half its current age, when stellar populations differed dramatically from those we observe today, when the Milky Way itself was still a young and chaotic stellar nursery, where violent processes dominated and the orderly rotation we observe today hadn't yet emerged from primordial chaos. The thick disk represents an older generation of stars that formed during the galaxy's early, turbulent period, roughly 10 to 12 billion years ago. Before the thin disk where our sun resides, had organized itself into the relatively orderly, co-rotating structure we observe today. Unlike the thin disk, where stars follow roughly circular orbits around the galactic center, like cars on a cosmic highway, the thick disk contains stars with more eccentric, tilted orbits that reflect the violent conditions of their birth era, when the galaxy was still settling into its current configuration. If 3I Atlas indeed originates from this ancient population, analysis of its velocity vector and approach angle, suggesting membership in this older stellar cohort, it carries within its nucleus a record of stellar neighborhoods that existed before our solar system was even a glimmer in a molecular cloud's eye chemical signatures from an era when the universe was younger and metal poor compared to current conditions. The scales of this journey become almost poetic when we attempt to visualize them through metaphors that ground cosmic timescales in human experience. 3I Atlas has potentially been wandering the galaxy for billions of years, a duration during which entire stellar generations have been born, lived, and died in supernova explosions that seeded space with heavy elements and triggered new rounds of star formation. Massive stars that existed when this object began its interstellar odyssey have long since exploded, their remnants now neutron stars, or black holes, their fusion products now incorporated into younger stars and planets that didn't exist when 3I Atlas first achieved interstellar velocity. Planetary systems have formed, evolved, and potentially developed life countless times over during this ancient wanderer's journey through the cosmic dark biological evolution, running its course on worlds that arose and fell, while this frozen remnant traced its lonely path through the galaxy. The travel times involved dwarf any human concept of duration or persistence. If 3I Atlas has indeed been wandering for 5 billion years, a conservative estimate based on its apparent thick disk origin and the time required to traverse galactic distances at its current velocity, it has been traveling for more than 1,000 times longer than complex life has existed on Earth. During its journey, our planet has experienced the Cambrian explosion that filled our oceans with diverse animal forms, 5 major mass extinctions that reset evolutionary trajectories and eliminated dominant species, the rise and fall of the dinosaurs across hundreds of millions of years, and the eventual emergence of human civilization in what amounts to the final microsecond of this wanderer's multi-billion-year voyage. Yet from the perspective of this cosmic traveler, all of human history represents merely the final fraction of a second in a journey lasting geological ages. Our entire civilization's existence compressed into a duration so brief it barely registers against the timescales involved. The distances traversed are equally staggering when we attempt to comprehend the sheer scale of interstellar travel. Even at 3I Atlas's tremendous velocity, exceeding 130,000 miles per hour, crossing significant portions of the galaxy, requires millions of years of continuous travel journeys, so long that the stellar landscape itself changes during transit, as stars complete multiple orbits around the galactic center. The object has potentially encountered hundreds or thousands of stellar systems during its wandering passing, close enough to some to be influenced by their gravitational fields, in encounters that slightly altered its trajectory through gravitational slingshot effects. perhaps even witnessing the birth of planets around stars that are now ancient giants nearing the ends of their lives, or already exploded into supernova remnants. These encounters would have been silent and unobserved, occurring in the depths of space, far from any witness capable of recording them, except possibly the object itself, if it somehow possessed memory or instrumentation, possibilities we've explored in speculation, but for which no evidence exists. Our own radio bubble, the expanding sphere of electromagnetic radiation that announces humanity's presence to the cosmos through leaked transmissions from radio and television broadcasts, radar installations, and other electromagnetic sources, provides a humbling perspective on these galactic scales and the difficulty of interstellar communication, even with deliberate effort. Since Marconi's first wireless transmissions in the late 19th century, our radio signals have been expanding outward at the speed of light, currently reaching stars within roughly 120 light-years of Earth, a sphere that sounds impressive until we realize that our galaxy spans roughly 100,000 light-years in diameter, making our radio presence a tiny bubble in the vast galactic ocean, barely perceptible against the cosmic background noise. This sphere contains perhaps a few thousand stellar systems out of the galaxy's estimated 400 billion stars, a fraction so small it's difficult to visualize, like a single grain of sand representing a tiny beach rather than a vast desert. Even our most powerful radio transmissions, designed to communicate across interplanetary distances within our solar system, would appear as faint whispers to any listeners around nearby stars, requiring radio telescopes of enormous size and sensitivity to detect across light years of space, where signal strength diminishes according to the inverse square law that makes electromagnetic radiation fade rapidly with distance. The idea that 3I Atlas might have been attracted to our solar system by our electromagnetic signature becomes implausible when we consider both the object's apparent age, predating our radio emissions by billions of years, and the minuscule fraction of the galaxy that our radio presence encompasses, a bubble so small it barely qualifies as a cosmic footnote in the galactic conversation we've joined so recently. 5 billion years compressed to human scale. If each year equals 1 second, 3I Atlas has been traveling for 158 years. Meanwhile, all of human history, from first agriculture to smartphones, occupies about 3 minutes of that journey. We are babies in cosmic time newcomers, so recent our entire species' existence wouldn't register as a meaningful duration to something that's been wandering since before our sun ignited and will continue wandering long after our sun dies. Our radio bubble, 120 light-years in a 100,000 light-year galaxy, is like shouting in a football stadium and hoping someone in Las Vegas hears you. Technically, the sound waves propagate that direction. Practically, not happening without amplification technology we haven't invented yet, and cooperative listeners we haven't confirmed exist. Perhaps the most profound gift that 3I Atlas offers humanity lies not in any exotic speculation about its origins or purpose, but in the simple fact of its non-threatening passage through our cosmic neighborhood, according to trajectories we predicted with precision behavior. We understood through physics and chemistry we can explain through natural processes, even when those processes differ from our local experience. In an era when global challenges can seem overwhelming and our future uncertain, there's something deeply reassuring about a cosmic visitor that arrives precisely when predicted, behaves exactly as natural laws dictate, and departs safely into the interstellar night without disrupting a single terrestrial sunset or requiring any defensive measures beyond the passive protection provided by the vast distances that separate its trajectory from our planetary orbit. This reassurance isn't trivial or mere comfort without substance. It represents the triumph of scientific understanding over cosmic anxiety, the victory of careful observation over unfounded speculation and paranoid fantasy. When 3I Atlas was first detected racing toward our solar system at unprecedented velocity, we might have feared the unknown succumbed to ancient threat detection systems evolved for terrestrial dangers rather than cosmic encounters. Instead, within weeks of discovery, international teams of astronomers had calculated its exact trajectory with precision measured in kilometers across astronomical unit distances, analyzed its chemical composition through spectroscopy that revealed molecular fingerprints, and confidently predicted its harmless passage based on celestial mechanics that have governed solar system dynamics for billions of years before humanity emerged to observe and understand those processes. The scientific harvest from 3I Atlas has already exceeded what most astronomical discoveries provide over their entire investigation, lifetimes yielding insights that will influence our understanding of planetary formation, cometary, chemistry, and galactic evolution for decades to come. The object's unusual carbon dioxide-rich composition has challenged our assumptions about typical comet chemistry, forcing researchers to develop new models for how volatile ratios might vary among objects formed in different stellar environments under conditions we've never directly observed. This isn't merely academic knowledge pursued for its own sake. It informs our understanding of planetary formation processes that operate throughout the galaxy, helping us predict what kinds of worlds might exist around different types of stars, and how the chemistry of life's building blocks might vary in environments radically different from our own solar system's history. The spectroscopic signatures revealed by the James Webb Space Telescope provide direct evidence for the kinds of chemical processing that occur around other stars, expanding our catalog of cosmic chemistry beyond the limited sample available from objects born in our own stellar neighborhood. The high carbon dioxide to water ratio observed in 3I Atlas's coma suggests formation near carbon dioxide snowlines in protoplanetary disks where temperatures and pressures favored CO2 condensation, or alternatively, radiation processing of surface materials over geological timescales that modified composition through cosmic ray bombardment and photochemical reactions driven by interstellar ultraviolet radiation. Either interpretation expands our understanding of the diversity of environments and processes that shape icy bodies beyond our solar system, teaching us that the universe produces variety we've only begun to catalog through the small sample of interstellar visitors we've detected so far. These chemical insights have implications extending far beyond cometary science into the search for habitable worlds, and the conditions that might support life as we know it, or perhaps life as we don't yet know it. Understanding how volatile inventories vary among objects from different stellar systems helps astronomers refine models of planetary formation and evolution that apply to the search for Earth-like worlds around other stars, informing predictions about where and when we expect to find conditions suitable for biology. If carbon dioxide-rich environments were common during certain epochs of galactic evolution, perhaps when metallicity was lower and stellar populations younger, this might influence where we search for biosignatures and what kinds of atmospheric compositions might indicate biological activity rather than purely geological processes. The institutional response to 3I Atlas has demonstrated the remarkable efficiency of modern astronomical coordination when confronted with unprecedented phenomena that demand rapid response and international collaboration. The Atlas survey detected the object using automated systems that scan the sky continuously for anything that moves against the stellar background. The Minor Planet Center coordinated global tracking efforts through established protocols that have evolved over decades of asteroid and comet discovery. The Hubble and Webb space telescopes provided detailed follow-up observations that required complex scheduling and operational coordination. Ground-based observatories contributed complementary data across wavelengths and observation geometries that no single instrument could provide, all within a time frame that would have been impossible just decades ago. Before digital communication, automated surveys and international collaboration became standard practice in astronomical research. This coordination extends beyond mere technological capability to represent a philosophical commitment to shared knowledge and collaborative investigation that transcends national boundaries and institutional rivalries. The decision to make observational data publicly available through standard astronomical archives like MAST reflects the scientific community's conviction that cosmic discoveries belong to all humanity rather than individual institutions or nations that happened to possess the instruments that detected them first. Such openness becomes particularly significant when studying objects that might, in principle, represent our first encounters with phenomena beyond terrestrial experience, where transparency builds trust and allows independent verification that eliminates conspiracy theories and ensures conclusions rest on evidence rather than authority. Think of it this way: the worst-case scenario for 3I Atlas was nothing dangerous happens, like worrying all week about a first date, and then they don't show up. Safe, definitely, disappointing, maybe a little, but ultimately the right outcome when the alternative involved genuine existential risk from objects racing through our neighborhood at cosmic velocities we couldn't deflect even if we wanted to intervene. We're near the end of this story. If you're still awake, why, just kidding. Thank you for your patience through thousands of words about what essentially amounts to a space rock that proves interesting but harmless. But that's the point, isn't it? Even just a space rock from another star system contains enough wonder to fill hours of contemplation, enough mystery to fuel speculation, enough reality to ground us in a universe stranger than fiction, but still comprehensible through patient observation and careful analysis. The Vera Rubin Observatory, currently under construction in Chile and scheduled to begin operations later this decade, will revolutionize our understanding of interstellar objects by detecting them at rates that transform these visitors from rare curiosities into routine astronomical phenomena we can study statistically rather than relying on tiny samples dominated by selection effects and observation biases. The observatory's Legacy Survey, Space and Time, will scan the entire visible sky every few nights using an enormous camera that captures images covering areas 40 times the size of the full moon in single exposures, detecting anything that moves, changes brightness, or appears where nothing existed before. This unprecedented survey capability should detect 1 to 2 interstellar objects per week once operations reach full capacity, providing hundreds of targets over the planned 10-year mission, rather than the mere 3 confirmed interstellar visitors we've accumulated over the past 8 years, since Oumuamua's discovery first proved that such detection was possible with current technology. From rare, just 3 objects total, each making international headlines, to common hundreds cataloged and characterized, represents a paradigm shift in interstellar object science, comparable to the transformation that occurred in exoplanet studies when the Kepler Space Telescope detected thousands of planets around other stars. With large statistical samples, astronomers can move beyond describing individual objects to identifying populations, classifying chemical groups, tracing origins to specific stellar environments, and reconstructing dynamical histories that reveal how these objects were ejected from their birth systems and what gravitational encounters shaped their trajectories during millions or billions of years of wandering. The Nancy Grace Roman Space Telescope, scheduled to launch later this decade, with infrared capabilities that complement Rubin's optical surveys, will enable detection of objects farther away and earlier in their approach, potentially finding interstellar visitors while they're still in the outer solar system, beyond Neptune's orbit, where they remain cold and relatively inactive. The James Webb Space Telescope will continue providing detailed spectroscopic analysis as new interstellar objects are discovered, building catalogs of molecular compositions and volatile ratios that reveal the diversity of chemistry in stellar environments we've never visited, teaching us what kinds of materials condense from protoplanetary disks around different types of stars, and how those materials evolve during billions of years in interstellar space. These combined capabilities, wide-field optical surveys, detecting objects, infrared telescopes, characterizing them from great distances, spectroscopic analysis, revealing chemical fingerprints, will transform interstellar object science from opportunistic studies of rare visitors into systematic investigation of a population we can analyze statistically to test theories about planetary system formation and galactic chemical evolution. If alien technology exists among the wandering population of interstellar debris, larger samples and better instrumentation will eventually expose artificial origins through subtle but persistent deviations from natural behavior, patterns, anomalies that might remain hidden in samples of 3 or 10 objects but become statistically significant when hundreds are compared against predictions from planetary formation models. Perhaps we'll find that all interstellar objects display chemical compositions explainable through natural processes, confirming that the universe produces variety without requiring intelligence to engineer exotic materials. Or maybe we'll detect outliers whose properties demand explanations beyond natural geology. Objects that display geometric structures, artificial isotope ratios, or behavioral patterns, inconsistent with passive cometary activity responding to solar heating. 3i Atlas represents precedent model and lesson for the next generation of interstellar object discoveries. It demonstrates the capabilities of our current observational infrastructure, while highlighting limitations that future instruments will overcome. It provides a template for international coordination and data sharing that should guide responses to even more unusual discoveries. And it reminds us that the universe still holds surprises that challenge our understanding without requiring wholesale revision of physics, discoveries that expand our knowledge in interesting directions while remaining comprehensible within frameworks built through centuries of patient observation and theoretical development. Vera Rubin. Observatory is like upgrading from fishing with a rod to industrial-scale netting. Suddenly, the fish market of interstellar objects transforms from occasional curiosities to regular catalogs we can analyze for patterns, rather than treating each detection as a unique event worthy of international headlines and speculation about alien origins. Your children's generation will study interstellar objects the way you studied planets, routine entries in textbooks, rather than rare wonders making news. From exotic to mundane in a single generation, which paradoxically makes them more scientifically valuable because statistical analysis requires sample sizes larger than 3 objects discovered over 8 years. The Great Silence continues. 3 interstellar visitors, all 3 natural none, displaying obvious signatures of technological origin despite our instruments' sensitivity and our willingness to consider extraordinary possibilities when evidence supports them. This persistent absence of artificial signatures forces us to confront 2 possibilities, neither comfortable, but both profound in their implications for our place in the cosmic order. Either we are genuinely rare, perhaps even unique in our galactic neighborhood, if not the observable universe, the only intelligence to have evolved and survived long enough to build telescopes and contemplate our cosmic loneliness. Or intelligence exists in abundance, but hides so effectively that detection remains impossible with our current capabilities, whether through deliberate concealment strategies motivated by dark forest logic, or simply because technological signatures fade rapidly or manifest in ways we haven't learned to recognize. Neither possibility is inherently frightening, despite initial emotional reactions that loneliness or being surrounded by hidden watchers might trigger. If we're alone, or nearly so, that makes our existence precious beyond measure. A cosmic lottery, won so improbably that our continued survival and flourishing becomes a responsibility to the universe itself, custodians of the only consciousness capable of observing and understanding cosmic evolution, at least in our local galactic volume. If we're surrounded by intelligences that remain hidden, that suggests they've survived long enough to develop sophisticated strategies for persistence, following physics and evolutionary pressures similar to those that shaped us, meaning the universe operates according to rules we can learn through observation rather than being fundamentally hostile or incomprehensible to scientific investigation. The dark forest remains philosophy rather than demonstrated strategy, a thought experiment about how rational actors might behave in situations of profound uncertainty rather than established fact about how cosmic civilizations actually conduct themselves. The absence of evidence for deliberate concealment, no signs that our radio emissions have triggered defensive responses, no indications that surveilling probes monitor our activities suggests that if the dark forest strategy operates, it operates at scales and timelines that don't particularly concern civilizations at our current development level. We remain below whatever threshold might trigger responses from more advanced neighbors, if such neighbors exist young enough and primitive enough that we're not yet worth noticing by intelligences that measure significance in capabilities we haven't developed. The Great Filter concept serves as a reminder that technological capability needs to be accompanied by wisdom sufficient to avoid self-destruction through misuse of powerful technologies. We're only beginning to develop nuclear weapons, artificial intelligence, climate disruption, synthetic biology, all represent dual-use technologies that could either elevate humanity to new levels of capability and flourishing, or destroy our civilization through accidental misuse or deliberate weaponization that spirals beyond control before we understand consequences. The filter reminds us that advancement brings risks, as well as opportunities, that development needs to be thoughtful and guided by ethical considerations, rather than pursued recklessly in competitive races that prioritize speed over safety. 3i Atlas teaches cosmic humility. We are small recent and operating within a universe vastly older and larger than our civilization's brief existence. But that humility shouldn't become paralysis or despair. The same observation that reveals our smallness also demonstrates our capacity for understanding, our ability to detect and analyze objects that have been traveling since before our sun ignited, to extract meaning from light that carries information across interstellar distances, to coordinate international efforts that transcend political boundaries in pursuit of knowledge that belongs to all humanity. Science becomes light in darkness, not claiming to solve every mystery or answer every question, but illuminating paths forward through systematic observation and careful reasoning that build understanding incrementally across generations. Curiosity remains more valuable than fear, as our fundamental orientation toward cosmic unknowns, unknowns that will always exist no matter how much we learn. The universe will always be stranger than we currently understand, always containing phenomena we haven't discovered and principles we haven't grasped. Maintaining wonder and openness while avoiding paranoid speculation that sees threats in every anomaly represents the balance that allows productive engagement with cosmic mysteries without descending into either complacent certainty or paralyzing anxiety about hidden dangers. We're like someone sitting in an empty cafe, wondering, am I early late? Or is this the wrong cafe entirely? That's humanity with the galaxy. We showed up expecting neighbors and found empty rooms. Plot twist. Maybe the cafe is still open, just not crowded. Maybe we are early, rather than late, the first customers in a restaurant that will eventually fill with conversations we can't yet imagine. Are you afraid of being alone in the universe? Or afraid of not being alone? Both fears are valid. Fear is a sign you're thinking rather than mindlessly accepting comfortable assumptions. The appropriate response isn't to eliminate fear, but to acknowledge it while proceeding with curiosity that overwhelms anxiety through active investigation rather than passive worry. As 3i Atlas continues its ancient journey outward from our sun fading with each passing day into the star-scattered darkness from which it came, it leaves behind more than just scientific data and published papers that will influence research for decades. The Hubble Space Telescope's exquisite portraits show a fuzzy, star-like point surrounded by the gossamer envelope of its carbon dioxide coma, a cosmic ornament suspended against the infinite black of space, an image that will endure in astronomical archives long after the object itself has disappeared beyond the reach of even our most powerful instruments. Webb's infrared vision reveals the molecular signatures of that coma in precise detail, each spectral line, a word in the ancient chemical language this visitor carries from its birthplace around another star in an era when our solar system didn't yet exist, and the galaxy was younger and wilder than the ordered structure we observe today. The trajectory plots tell their own story of cosmic choreography, smooth curves, arcing across diagrams showing 3i Atlas's path through our solar system past Mars's orbit at closest approach around the Sun, at perihelion, where solar heating drives spectacular outgassing, and back out toward the realm of the gas giants, before continuing into interstellar space, where it will wander for perhaps another billion years, before encountering another stellar system, or perhaps never encountering anything again except the thin dust and occasional molecular clouds that occupy the space between stars. These aren't the chaotic, unpredictable paths of human political or economic events subject to whim and irrationality, but the serene precision of celestial mechanics, as inevitable as sunrise and as dependable as the season's trajectories determined billions of years ago by initial velocities in gravitational encounters that continue playing out according to laws that have governed motion in space since the universe began. There's something deeply satisfying about this predictability, this cosmic reliability that operates beyond human influence or control, immune to our politics and unaffected by our concerns. While our terrestrial world churns with uncertainty and manufactured urgency designed to capture attention in competitive information environments, 3i Atlas follows laws that have governed motion in space since the universe began, laws we can understand through mathematics and verify through observation, laws that don't change based on opinion or belief, but simply operate with absolute consistency across cosmic distances and timescales. Its departure is scheduled not by human decision, but by the fundamental forces that shape reality itself, momentum and gravity, interacting according to equations we can write on paper and solve with computers to predict positions years in advance with accuracy measured in kilometers. In an age of manufactured anxiety and artificial urgency, where every news cycle brings fresh reasons for concern, such cosmic dependability offers a profound form of comfort that transcends daily worries and political controversies. The answer to our investigation's central question, what's the worst that could happen, has proven refreshingly mundane when measured against Hollywood disaster scenarios our primitive threat detection systems might conjure. No catastrophe awaits. No alien invasion threatens our civilization. No cosmic disruption will alter Earth's orbit or climate. The worst case in terms of actual physical threat is quite literally nothing at all. 3I Atlas will depart our solar system exactly as it arrived, silently, safely, and according to the precise predictions of mathematical physics that describe its motion with accuracy, that leaves no room for surprise or deviation. But perhaps calling this outcome mundane misses its true significance and understates the profound accomplishment this represents. The fact that we can predict the behavior of an object that has traveled for possibly billions of years, that formed around a star we've never seen, that carries chemical signatures from environments we've never directly studied. This predictability represents one of science's greatest triumphs, confirmation that the laws of physics operate with such consistency that phenomena separated by cosmic distances and geological time still follow the same fundamental rules. The universe is comprehensible through patient observation and careful reasoning, stranger than we imagined, but not so strange that it defies understanding or operates according to arbitrary principles that change based on location or observer. The universe is vast, strange, full of wonders we're only beginning to discover and understand. But this particular wonder, 3I Atlas, our third confirmed interstellar visitor, passes harmlessly through our neighborhood, a messenger from ancient times, carrying lessons we're only beginning to understand, leaving us with questions that will echo long after it disappears back into the darkness between stars where it wandered alone for longer than our sun has burned. Good night, cosmic messenger. Thank you for the data, the lessons, the reminder that the universe remains far stranger and more wonderful than our earthbound imaginations might suggest, without the discipline of observation and the humility to let evidence guide our conclusions. Safe travels on your continued journey through the galaxy, carrying whatever chemical secrets and ancient memories remain locked within your nucleus testimony to stellar environments and formation conditions that existed long before our world knew the warmth of its own star. Until we meet your cousins from other distant systems, other ancient epochs, other corners of the cosmic wilderness that surrounds our small but remarkable planetary home, sleep well, human listener. The universe is safe tonight. 3I Atlas has passed, and somewhere out there among the 400 billion stars of our galaxy, other ancient wanderers continue their journeys, perhaps carrying secrets we'll discover in decades or centuries to come, perhaps remaining forever silent and mysterious, but always reminding us that we inhabit a universe larger and older and stranger than we can fully comprehend, yet still knowable through the patient application of human curiosity and scientific method that turns cosmic mysteries into understood phenomena, one careful observation at a time. 270 million kilometers distant, 5 billion years old. Safe, absolutely mathematically, certainly safe. The universe vast and strange, and full of wonders. This particular wonder passes harmlessly, a messenger from ancient times. Questions that echo long after it disappears, back into darkness, between stars, where it wandered alone, longer than our sun has burned. Safe, safe, safe.